Hello there, and welcome to Science for Sleep, where curiosity gets cozy and science drifts gently alongside your thoughts. Tonight, we are going to take a long, unhurried journey out into the cosmos to explore a place that stretches far beyond our everyday imagining, a sprawling neighbourhood of galaxies, clusters, and invisible threads that connect it all. It is a region so vast that words feel small, so intricate that numbers start to blur, and yet it holds our own Milky Way within its grasp. Tonight, the gentle voyage is all about the Virgo Supercluster and the astonishing scale of the space we call home, the dimensions that reach far past our ordinary sense of distance, and the quiet enormity that exists just beyond our night sky. Before we begin to drift into the depths of billions of light years, I wonder, where are you listening from right now? Perhaps you're perched somewhere quiet, tucked under a blanket with a warm drink, or maybe you're sitting in a softly lit room with the window open to a fading sky. Either way, in this moment, you share a place in time with countless others who are also pondering the cosmos, scattered across cities, towns, and continents, yet all arriving here together in this very instant, ready to stretch your minds into the universe. If this gentle exploration feels like a calm retreat, if it offers a little pause from the pace of your day, I would be ever so grateful if you gave the video a like or maybe pressed subscribe. That quiet gesture helps this little corner of calm reach more people who might need a soft space to drift into thought too. Now, settling in, we can start by imagining the familiar sight of the night sky. Perhaps you can picture the Milky Way stretching across the darkness above, a mist of stars like sugar dusted over black velvet. Our galaxy, massive as it seems from here, is in fact only one of hundreds of billions of stars and planetary systems, and yet it is just a single resident of a much larger family. That family is known as the Local Group, a gathering of galaxies including Andromeda, Triangulum, and dozens of smaller companions. The Local Group itself is, however, only a small part of something far more immense. Stretching hundreds of millions of light years across, woven together in a web of gravity and motion, lies the Virgo Supercluster, our cosmic city of galaxies, whose boundaries are defined not by streets or walls, but by invisible currents of mass and energy that guide the motion of entire galactic clusters. The Virgo Supercluster is often described as a collection of clusters of galaxies, each cluster a dense hub of thousands of galaxies, bound together by gravity, yet moving with quiet individualism, orbiting the common centre like dancers following a rhythm that is both precise and mysterious. Our own Milky Way orbits around the Virgo cluster at a distance that is both immense and intimate. Some 50 to 60 million light years away. That distance is so vast that even light, the fastest thing in the universe, takes decades to travel from one end to the other. When we look at distant galaxies in the Virgo Supercluster, we are not just seeing points of light, we are seeing the echoes of the past, snapshots frozen in the glow of stars that formed millions or even billions of years ago. As you listen, consider the scale of numbers involved. The Virgo Supercluster contains roughly 100 galaxy groups and clusters. Each cluster can have thousands of galaxies. Every galaxy contains billions of stars. When we start to multiply these figures, the mind starts to wobble, not from confusion, but from awe. The stars we see at night are a tiny fraction of the galaxies that populate this supercluster, and yet those distant lights are connected in a web that shapes the motion of our own galaxy. Gravity, imperceptible to us in daily life, orchestrates these vast motions, tugging gently on our Milky Way and countless neighbours, nudging them ever so slightly toward the common centre, which itself is a swirl of matter and dark matter, invisible yet commanding. Perhaps it is helpful to imagine the Virgo supercluster not as a solid shape or a simple sphere, but more like a sprawling city viewed from high above. There are bustling centres, the clusters, where galaxies crowd together, surrounded by quieter suburbs, the galaxy groups, and threaded throughout are the highways and streets of dark matter filaments, invisible paths along which galaxies travel. And yet, even in this vastness, there is structure. It is neither random nor chaotic, but an intricate pattern that forms over billions of years through the slow, patient work of gravity. Every galaxy, including our own Milky Way, follows this cosmic choreography, moving in ways that seem imperceptible to us, but are measurable with precise instruments and patient observation. Distance, however, is only one part of the story. When we speak of the Virgo Supercluster, we are also speaking of time. Light travelling from its most distant galaxies takes millions of years to reach us. That means when we gaze at an image of a galaxy at the edge of the supercluster, we're not seeing it as it is now, but as it was long before humans walked the Earth, before continents formed their current shapes, before the oceans took the forms we recognise today. In a sense, looking at the Virgo Supercluster is like looking at a deep and ancient photograph, one taken over a span of time so vast that it dwarfs the entire history of our planet. Every photon carries a story from the past, arriving at our telescopes or our eyes after an epic journey across unimaginable space. And yet, despite the enormity, it is possible to find intimacy here. The Milky Way, with its familiar spiral arms and neighbouring galaxies, is one small participant in this immense structure. Our galaxy does not simply float, it orbits the centre of mass of the local group, which itself orbits the centre of the Virgo Supercluster. Every star, every planetary system, every speck of cosmic dust is influenced, however subtly, by the larger mass of the supercluster. When astronomers measure the motion of galaxies toward the Virgo cluster, they find a gentle pull, a cosmic current that guides movement over tens of millions of light years. The universe is not static, even on these enormous scales. Everything moves, everything shifts, everything participates in a quiet but ceaseless dance that has continued since the earliest galaxies formed. Observing the Virgo supercluster also gives insight into the greater cosmic web. Superclusters are not isolated islands in space. They are interconnected through filaments of galaxies and dark matter, stretching across hundreds of millions of light years. These threads guide the growth of clusters, direct the flow of gas, and influence the formation of stars and galaxies. In this web, the Virgo supercluster is a prominent node, a hub of activity that connects to other superclusters and voids, forming a lattice that spans the observable universe. Understanding this connectivity is one of the keys to comprehending the large-scale structure of everything we see, the patterns that govern the formation of galaxies and the movement of matter on scales far beyond our daily perception. Perhaps at this point you might wonder how astronomers even begin to measure such vastness. They rely on a combination of distance indicators, such as Cepheid variable stars, redshift measurements, and observations of galaxy motion. Each technique adds a piece to the puzzle, revealing not just the positions of galaxies but their velocities, their groupings, and their place within the larger structure. Through decades of careful observation, mapping, and calculation, humanity has managed to chart the Virgo supercluster with remarkable precision, transforming what was once unimaginable into a comprehensible, if still awe-inspiring map of our cosmic neighbourhood. Even so, numbers alone cannot capture the feeling of scale. When we speak of a supercluster stretching hundreds of millions of light years, it can feel abstract, almost unreal. To put it in perspective, if the Milky Way were the size of a single grain of sand, the Virgo supercluster would span an entire continent. Even more, the supercluster contains enough galaxies that if you tried to count them one per second, you would spend thousands of lifetimes and still not finish. The mind, accustomed to human scales, struggles with this enormity. Yet it is precisely this struggle that invites awe, wonder, and a sense of quiet humility. As we prepare to explore the Virgo supercluster further, it is worth noting that our understanding is still evolving. New telescopes, surveys, and computational models continue to reveal previously unseen galaxies, dark matter structures, and dynamic behaviours. The more we learn, the more intricate the picture becomes. It is as if each new discovery adds another brushstroke to a cosmic painting that is far too large for any one observer to fully comprehend, yet somehow through patience, curiosity, and careful observation, we can glimpse the harmony of its composition. So as you settle deeper into your seat, perhaps under a dim lamp or with the soft hum of night surrounding you, consider that your awareness, your imagination, and your curiosity are reaching across the same stretches of space that have taken millions of years for light to traverse. Every thought you have about the Virgo Supercluster connects you to that vast structure, and in a small, quiet way, you are part of the story of the cosmos. The universe is enormous, yes, but it is not indifferent. It is a place where galaxies gather, stars are born and die, and human consciousness can reach out to understand, to measure, and to wonder. Let's linger for a moment in the neighbourhood of galaxies that surrounds our own Milky Way. This neighbourhood, while unimaginably vast by human standards, is intimate in cosmic terms, a small corner of the universe where motion, gravity, and light shape a delicate balance. The Milky Way itself is part of a collection of galaxies known as the Local Group, a gravitationally bound cluster of about 50 known galaxies. Within this group, a few stand out for their sheer size and presence, such as the Andromeda Galaxy, a spiral giant with a mass slightly larger than our own, and the Triangulum Galaxy, a more modest spiral, yet remarkable for its proximity and dynamic interactions. Many of the other members are dwarf galaxies, small and faint, orbiting their larger companions like satellites caught in a subtle cosmic dance. In this neighbourhood, interactions are constant, though they are gentle and slow on human timescales. Galaxies approach, sway around each other, and occasionally merge in a process that can take hundreds of millions of years. These mergers are not violent in the way we imagine collisions on Earth. Instead, they are gradual, orchestrated by gravity, a slow intertwining of stars and gas that can trigger bursts of star formation, shift orbits, and slowly reshape the structure of entire galaxies. The Milky Way itself bears the marks of past encounters, streams of stars tracing the remnants of swallowed companions, silent evidence of a history that is both complex and ongoing. When we map the Local Group, it becomes clear that it is more than just a random collection of galaxies. There is structure, a hierarchy that mirrors the larger universe. At the centre, the Milky Way and Andromeda dominate in mass and influence. Around them orbit smaller satellites, some tiny, almost ghostly, only detectable with sensitive instruments. Others more substantial, like the large and small Magellanic Clouds. These satellites are not mere decoration. They participate in the gravitational rhythms of the group, tugging on their hosts and being tugged in turn. Their motions tell a story of interactions and influences that span billions of years, a story that connects our galaxy to the broader cosmic web. Beyond the Local Group, other galaxy groups form a broader neighbourhood. The M81 group, the Sculptor group, and the Centaurus A group are nearby collections that, while separated by millions of light years, are linked in motion and structure to our own Local Group. Observing these groups is like looking at houses in a suburban block, each with its own yard, its own routines, and yet connected by streets, pathways, and the invisible pull of gravity. The distances between groups are immense, but the same forces that bind the Local Group also operate on these larger scales, guiding clusters of galaxies toward one another, shaping their paths, and slowly sculpting the universe over cosmic time. It is important to pause and consider just how small the Local Group is within the grand structure of the Virgo Supercluster. Even though the Milky Way feels like a vast universe in itself, with hundreds of billions of stars and countless planets, the Local Group is but one small neighbourhood, a single node in a much larger cosmic network. The Virgo Supercluster contains around 100 groups and clusters like our own local group, each with their own galaxies, each moving along their own paths, yet all bound together by the combined gravitational influence of the supercluster. When we imagine the Virgo Supercluster, it helps to picture countless neighbourhoods like ours, each bustling with stars yet forming a pattern so vast that the mind struggles to encompass it all. The interactions within these neighbourhoods are subtle, yet they leave lasting effects. Galaxies in groups often experience tidal forces from their neighbours, gentle pulls that stretch and distort their shapes. Spiral arms can warp, gas can be stripped, and star formation can accelerate or slow depending on proximity to a larger galaxy. In some cases, entire dwarf galaxies are absorbed, leaving only streams of stars as evidence. These processes happen slowly, invisibly, and yet they are the mechanisms by which galaxies evolve, by which the universe organizes itself over time. Observing these interactions, astronomers can reconstruct the past trajectories of galaxies, predict future mergers, and understand the delicate balance that keeps a neighbourhood like ours in motion without descending into chaos. Looking outward, the local group is moving toward the centre of the Virgo Supercluster at a speed of roughly 1,100 kilometers per second, pulled by the gravitational influence of countless unseen masses. This motion is slow on human timescales, but relentless, a constant drift that has been occurring for billions of years. The Milky Way and Andromeda are on a collision course, a meeting that will take place in approximately 4 billion years. This future event, while distant, is a reminder that even seemingly stable neighbourhoods are dynamic, that every galaxy, no matter how solitary it seems, is part of a larger conversation, a cosmic story written in motion and gravity. Even within a single galaxy, the interactions with its neighbours can have profound consequences. The streams of stars stripped from smaller companions create faint ribbons that wrap around the galaxy, sometimes forming arcs that span tens of thousands of light years. Gas clouds pulled from these companions can fuel bursts of star formation, lighting up regions of the galaxy with brilliant new stars that will shine for millions of years. These processes are subtle in real time, but over cosmic timescales, they shape the evolution of galaxies, determining their structure, composition, and even the potential for habitable worlds. The Milky Way itself bears the imprints of several such interactions, reminders of a long history of encounters that continue to this day. Beyond our local group, clusters of galaxies provide a denser environment where interactions are even more pronounced. In clusters like Virgo, galaxies are packed more tightly together, moving at higher velocities and experiencing stronger gravitational influences from one another. Collisions, while still slow compared to human perception, are more frequent, and the effects on galactic evolution are more dramatic. Galaxies in these dense neighbourhoods often have their gas stripped away, halting star formation, while others merge to form larger elliptical galaxies. Observing these clusters gives insight into the forces that shape the universe on a scale far beyond individual galaxies or groups, and allows us to understand the mechanisms by which superclusters like Virgo grow and change over time. The neighbourhood of galaxies is also filled with the unseen. Dark matter, invisible yet dominant in mass, forms the scaffolding upon which galaxies assemble. Every galaxy in the local group sits within a halo of dark matter, a gravitational shell that guides motion, shapes orbits, and influences interactions with neighbours. Without these halos, the motions we observe would not make sense. Dark matter is not just a backdrop, it is an active participant in the neighbourhood, a quiet but essential force that organises the visible universe and allows structures like the Virgo Supercluster to form and persist. And light itself carries the stories of this neighbourhood. When we observe Andromeda, we see it as it was approximately 2.5 million years ago, long before humans existed on Earth. The Triangulum Galaxy offers a window into a time roughly 3 million years in the past. Every photon reaching our telescopes has travelled across the neighbourhood for millions of years, connecting us directly to distant regions, providing snapshots of motion, interaction, and change. Through careful observation, astronomers can map the velocities, distances, and trajectories of galaxies, revealing the intricate choreography that unfolds across millions of light years, a dance dictated by gravity, mass, and motion. Even as we contemplate these enormous scales, there is intimacy in understanding the neighbourhood. The local group, small though it may be in the cosmic context, is our immediate environment. It is the setting for the Milky Way's motion, the backdrop against which our galaxy orbits, collides, and evolves. Observing the motions of nearby galaxies allows us to measure mass, infer the presence of dark matter, and predict future encounters. It is a neighbourhood where cause and effect are tangible, where the invisible influence of gravity is made visible through motion and structure, and where the universe, though immense, feels just a little closer, a little more comprehensible. And so, as we drift outward from our Milky Way, moving past familiar companions like Andromeda and Triangulum, past dwarf satellites and streams of stars, we can begin to sense the larger patterns that define the Virgo Supercluster. The local group, while small, is part of this vast structure, connected to other groups and clusters through threads of gravity, motion, and time. The neighbourhood of galaxies is both a window and a doorway, offering a perspective that is immediate yet expansive, intimate yet awe-inspiring, and inviting us to follow the paths of light and motion deeper into the grand structure that surrounds us. As you breathe, allowing these images to form softly in your mind, consider the connections that reach across millions of light years, the subtle tugs and shifts that shape entire galaxies, and the quiet, persistent flow of motion that guides the local group toward the Virgo cluster at the centre of the supercluster. Each galaxy, each star, each invisible stream of dark matter participates in this grand architecture, and yet within this enormity there is a rhythm, a pattern, a gentle order that invites observation, curiosity, and wonder. The neighbourhood of galaxies is not just a location, it is a story, a network, a living system that stretches outward, carrying our Milky Way along paths dictated by forces we can measure, yet still marvel at, connecting our small corner of the universe to the vastness beyond. If you glance upward on a clear night, away from the bright city lights, you may notice a faint haze of stars stretching across the darkness, an unbroken swath that hints at the vastness beyond our immediate surroundings. In this quiet, you can begin to orient yourself toward the Virgo Supercluster, an immense structure that is both nearby in cosmic terms and staggeringly distant in human perception. Locating Virgo is not about spotting a single point of light, but sensing a region, a neighbourhood in the sky where thousands of galaxies cluster together, a gentle glow in the constellation that bears its name. The Virgo cluster, at the heart of the supercluster, is the anchor point, a dense assembly of galaxies that collectively shine faintly, yet with significance that extends across millions of light years. Rather than attempting to pinpoint an exact location immediately, it helps to consider the sky as a map, with constellations serving as familiar guideposts. Virgo, one of the largest constellations, stretches across a broad portion of the sky. Its stars, visible even to the unaided eye in dark conditions, form a subtle pattern that has guided observers for millennia. Among these stars, the bright Spica marks a convenient reference, shining with a blue-white intensity that stands out against the softer backdrop of surrounding points of light. Spica acts as a beacon, a celestial guidepost that hints at the greater, more complex structure hidden just beyond naked eye perception. As you imagine tracing the lines of the constellation, you can start to appreciate the vast scale involved. The galaxies that comprise the Virgo cluster are not mere stars. They are entire systems, each with billions of suns, planetary systems, nebulae, and the faint glimmers of gas and dust. Many of these galaxies are elliptical, massive and rounded in form, while others are spirals like our Milky Way. their arms swirling in elegant patterns shaped over billions of years. Observing them requires powerful instruments, yet even knowing that they exist in a defined region of the sky gives a sense of the organization and scale of the supercluster as a whole. Beyond identifying the Virgo cluster itself, it is important to understand that it is part of a larger network. The Virgo supercluster is not a single compact entity. Instead, it is an assembly of multiple galaxy groups and clusters connected through space and gravity, forming a structure that stretches over roughly 110 million light-years in diameter. When astronomers study this region, they see not just points of light, but the gravitational relationships among galaxies, the flows of matter, and the subtle effects of dark matter guiding the motions of these cosmic neighbours. In locating Virgo, you are locating a region where order emerges from vast distances, a place where the motions of countless galaxies converge in patterns that are measurable, predictable, and yet endlessly fascinating. Using modern telescopes, astronomers can map the positions of individual galaxies within Virgo. The cluster contains more than 2,000 known members, and this number continues to grow as more faint and distant systems are detected. Each galaxy contributes to the collective mass and gravitational pull of the cluster, influencing the paths of nearby neighbours and participating in the intricate cosmic dance that defines the supercluster. Even our local group, with the Milky Way and Andromeda at its centre, is subtly affected by the mass of Virgo, drifting slowly toward its centre over the course of billions of years. These motions, imperceptible on human timescales, are measured using the redshifts of galaxies, tiny shifts in light caused by their velocity relative to us, a delicate technique that allows astronomers to chart motion and distance across millions of light-years. Beyond the Virgo cluster, other subclusters and galaxy groups occupy the supercluster. The Leo cluster, Coma cluster, and smaller aggregations form a network that stretches across the sky and defines the supercluster's boundaries. Observing these structures reveals that superclusters are not isolated. They are interconnected, forming the scaffolding of the cosmic web. Filaments of dark matter stretch between clusters, guiding the formation of new galaxies and the motion of existing ones. These invisible threads, though unseen by our eyes, exert influence on scales far beyond the reach of intuition. By locating Virgo in the night sky, we are also tracing the outline of a vast interconnected network that defines structure in the universe. Considering the scale involved is essential. While the stars in the night sky appear fixed and familiar, the galaxies of Virgo occupy distances that are difficult to comprehend. Light from the Virgo cluster takes roughly 50 to 60 million years to reach Earth. That means when we observe the cluster, we are seeing it as it existed long before humans existed, long before complex life appeared on Earth, and long before our planet had continents in their current form. Each observation is a journey back in time, a connection across an immense expanse, reminding us that the universe is not static but a dynamic entity, in which motion, evolution, and change are constants. The process of finding Virgo also invites reflection on the tools humans have developed to navigate the cosmos. From early astronomers charting constellations to modern instruments measuring redshifts and galaxy motions, our ability to locate structures like Virgo relies on ingenuity, patience, and observation. Large-scale surveys, such as the Sloan Digital Sky Survey, have mapped millions of galaxies, allowing us to identify the boundaries of superclusters, the density of galaxy populations, and the intricate flows of matter shaped by gravity. Without these instruments, the Virgo supercluster would remain a distant idea, an abstract collection of galaxies beyond comprehension. With them, it becomes tangible, something we can observe, measure, and contemplate, even if only in images and calculations. Yet, even as instruments extend our vision, there remains a sense of intimacy in locating Virgo. Knowing the direction to Spica, tracing the pattern of the constellation, and understanding that billions of galaxies lie in that general region connects us personally to the universe. Our position in the local group, orbiting the Milky Way, situates us within the gravitational embrace of the Virgo supercluster. and our observations link us directly to the motions and history of countless distant galaxies. The act of locating Virgo is both practical and meditative, a way of situating ourselves in a vast, ordered yet dynamic cosmos. As we mentally map the cluster, it helps to consider the variations among its members. The Virgo cluster contains a mix of galaxy types. Spiral galaxies, like M87's smaller companions, display swirling arms and active star formation. Elliptical galaxies dominate the dense central regions, older and less active, their stars moving in smooth orbits around the cluster center. Irregular galaxies, though fewer, add diversity to the population. Each galaxy type offers clues about the environment, past interactions, and the gravitational history of the cluster. Observing these variations allows astronomers to understand how clusters like Virgo evolve over time, how galaxies grow, merge, and adapt to the cosmic neighborhood they inhabit. Distance measurements play a crucial role in locating Virgo as well. Astronomers use Cepheid variables, supernovae, and redshift surveys to determine how far individual galaxies lie from us and from the center of the cluster. These techniques reveal a three-dimensional structure, showing that Virgo is not flat or uniform, but rather a complex, elongated collection of galaxies. The cluster is densest at its center, where gravity draws members into close proximity and becomes sparser toward the edges, gradually merging with surrounding groups. This three-dimensional mapping allows us to understand the gravitational interactions that shape motion and structure, and to trace the connections between Virgo and neighboring clusters. As you follow this journey, it may be helpful to imagine the Virgo Supercluster as a city at night, viewed from a distance. The brightest lights indicate major hubs, central clusters, and elliptical galaxies, while fainter glimmers mark smaller galaxies and satellites. Streets and highways are represented by dark matter filaments, invisible yet essential to the overall structure, guiding motion and connecting hubs. From this perspective, locating Virgo becomes more than finding a spot in the sky. It becomes a meditation on scale, structure, and connectivity, a way to appreciate the subtle yet pervasive forces that shape the universe. Observing the Virgo supercluster also emphasizes the passage of time on cosmic scales. Light from the farthest members has traveled for tens of millions of years, showing the galaxies as they were long before our solar system existed. In studying their motions, astronomers can predict future interactions, the eventual mergers of groups, and the evolution of clusters. The Virgo supercluster is a living, changing environment, where motion and gravity act across incomprehensible distances, and locating it is an exercise in both observation and imagination, linking us to events that span epochs beyond human experience. We are tiny observers within a vast structure, yet our ability to perceive, measure, and contemplate this immense neighborhood is a testament to curiosity, patience, and the capacity for wonder. Finding Virgo is not about marking a spot. It is about connecting to the rhythm, motion, and scale of a neighborhood of galaxies, each with its own story, yet all participating in the grand tapestry of the universe. To understand the Virgo supercluster, it helps to step back and think about what exactly a supercluster is. Unlike the neat ordered lines of a city or the familiar contours of a landscape, a supercluster is a vast, sprawling assembly of galaxies, groups, and clusters, all bound together by gravity, yet separated by distances so enormous they defy easy comprehension. These structures are not fixed or rigid, but dynamic, constantly evolving as galaxies move, merge, and interact with one another over millions or even billions of years. At its core, a supercluster is a way of describing regions in the universe where the density of galaxies is higher than average, where gravity has pulled together multiple clusters and groups, forming a web of matter that can stretch across hundreds of millions of light years. When astronomers talk about superclusters, they're referring to a hierarchy of structure. Galaxies themselves are the fundamental units, islands of stars, gas, dust, and dark matter. These galaxies often cluster together into groups, typically containing a few dozen to a few hundred members, orbiting around a common centre of mass. Multiple groups then coalesce into clusters, denser and more massive, with thousands of galaxies bound together. Finally, clusters and groups aggregate to form a supercluster. This multi-tiered organisation is guided by gravity, the quiet, persistent force that shapes structure across cosmic scales. The Virgo Supercluster is an excellent example of this hierarchy in action. It contains dozens of galaxy groups, multiple clusters including the central Virgo cluster, and countless individual galaxies, all participating in a slow, complex dance dictated by mass and motion. Examining the concept more closely, one notices that superclusters are not isolated. They are part of the cosmic web, the large-scale structure of the universe, which consists of filaments of galaxies separated by enormous voids. These filaments act like invisible highways, guiding the motion of matter over immense distances. Gravity pulls galaxies along these filaments, directing clusters toward one another and influencing the overall shape of superclusters. In this sense, superclusters are nodes within a vast interconnected network. They are regions of higher density within the universe's scaffold, yet they are connected to other superclusters through these faint but powerful cosmic strands. Understanding what makes a supercluster, therefore, involves not only counting galaxies, but tracing the invisible architecture of space itself, where matter is organized in ways that are subtle, complex, and profoundly ordered. The Virgo Supercluster, as we consider it, is not simply a collection of galaxies in proximity. Its definition relies on observing both density and motion. Galaxies within a supercluster are influenced by the combined gravitational pull of the structure, moving in patterns that reflect the mass distribution. Observers note that galaxies on the outskirts move toward the cluster centres, though these motions are slow and imperceptible on human timescales. Within the Virgo cluster, galaxies are densely packed, while farther out the supercluster stretches across tens of millions of light-years, gradually thinning into groups and isolated systems. The precise shape of a supercluster can be difficult to determine because boundaries are not defined by solid walls, but by the decline in galaxy density. In this way, superclusters are both vast and fluid, defined by patterns of gravity and matter rather than hard edges. Another defining feature of a supercluster is its diversity. Within the Virgo supercluster, one finds spiral galaxies like our Milky Way, with star formation actively ongoing, alongside massive elliptical galaxies whose stars have long since aged and cooled. Irregular galaxies and dwarf satellites add further complexity, creating a mix of structures and sizes that form the tapestry of the supercluster. The interactions among these members are subtle yet significant. Gravity causes galaxies to orbit, to sway, to merge, sometimes triggering bursts of star formation or creating long tidal streams of stars and gas. These interactions are indicators of the dynamism inherent in superclusters, revealing how structure is maintained even as the universe continues to expand. Mass plays a crucial role in defining a supercluster. It is not simply the number of galaxies that matters, but the total gravitational pull that arises from all matter, both visible and invisible. Dark matter dominates this mass, forming halos that envelop clusters and filaments, shaping the motions of galaxies and providing the scaffolding upon which the supercluster is built. Gas between galaxies contributes additional mass, often in the form of hot, ionized plasma that emits faint X-rays detectable by space telescopes. Together, visible matter, gas, and dark matter create the combined gravitational influence that holds the supercluster together, directing the motion of galaxies over millions of light-years and across spans of time that dwarf human experience. Looking at the structure of a supercluster from above, one sees not a sphere, but an elongated, often irregular shape. gravity draws galaxies together in filaments and clusters, but the overall form is stretched, shaped by interactions, mergers, and the ongoing expansion of the universe. The Virgo Supercluster, for instance, appears roughly flattened, with the densest region centered on the Virgo cluster itself. Surrounding groups and clusters extend outward, tapering into filaments that connect to other parts of the cosmic web. Mapping this shape requires a combination of observations, including galaxy counts, redshift measurements to determine velocity, and careful analysis of motion over large scales. The resulting picture is both ordered and complex, demonstrating that superclusters are not merely random collections, but structured regions reflecting the underlying forces that shape the cosmos. Time also defines what makes a supercluster. The universe is expanding, and superclusters are evolving along with it. Galaxies move slowly toward dense centers, sometimes merging, sometimes being ejected along filaments. These motions occur over billions of years, creating a dynamic system that changes subtly but persistently. Studying superclusters gives insight not only into spatial relationships, but also into cosmic history. The Virgo Supercluster is a snapshot of ongoing processes, showing the distribution of galaxies as they have developed over billions of years, influenced by gravity, cosmic expansion, and the interplay of visible and invisible matter. Understanding its formation requires looking at the past and imagining the future, tracing the evolution of structure across epochs that far exceed a human lifetime. Astronomers use a variety of methods to identify superclusters. Surveys of galaxy positions and velocities reveal regions of higher density. Mapping the distribution of dark matter through gravitational lensing shows where mass is concentrated, even when visible galaxies are sparse. Observations across different wavelengths from optical to X-ray help identify clusters, gas, and other components. By combining these measurements, scientists can define the boundaries, mass, and membership of a supercluster. These techniques show that superclusters are not merely conceptual, but measurable entities with structure, dynamics, and physical influence. The diversity within a supercluster also reflects environmental effects. Galaxies in dense central regions often have little gas, star formation slowed or halted, while those in sparser outer areas continue to form stars actively. Interactions and mergers are more frequent in the central regions, shaping galaxy morphology over time. Even faint dwarf galaxies, easily overlooked, play a role in the dynamics, contributing to tidal streams, gravitational interactions, and the overall mass of the system. The supercluster is a living network, each galaxy a participant in a slow, ongoing evolution, dictated by forces operating across unimaginable distances. Scale is a final, essential element in defining a supercluster. While galaxy groups may stretch tens of thousands of light years, clusters can span millions, and superclusters extend across hundreds of millions. The Virgo Supercluster, for instance, reaches roughly 110 million light-years in diameter, a scale almost impossible to visualize. Within this space, hundreds of groups and clusters move under shared gravitational influence. Light takes tens of millions of years to traverse even a portion of this structure, meaning that observation is always a journey into the past. Each measurement, each telescope image, each calculated orbit connects us to events and motions that unfold far beyond human perception, creating a sense of intimacy with an environment that is otherwise incomprehensibly vast. Understanding what makes a supercluster, therefore, is not just about counting galaxies. It is about recognizing hierarchy, motion, mass, interaction, and scale. It is about seeing connections among galaxies, clusters, and groups, understanding the subtle influence of dark matter, and tracing the flow of matter across cosmic distances. Superclusters are dynamic systems, evolving over billions of years, and yet through careful observation, they can be mapped, analysed, and appreciated in their full grandeur. From this perspective, the Virgo Supercluster is a neighbourhood, a city of galaxies interconnected through motion, gravity, and the invisible architecture of space. By identifying its members, tracing its boundaries, and observing its dynamics, astronomers reveal not only structure but also the processes that shape the universe. The supercluster is both enormous and intimate, a context in which our Milky Way resides, influenced by distant neighbours, moving ever so slowly toward the centre of gravity, a participant in a complex dance of matter and time. Imagine for a moment floating above the universe, far enough to see our Milky Way not as a sprawling collection of stars but as one of countless points in a grand cosmic ocean. In this vast space, galaxies stretch out in all directions, not isolated islands, but part of a flowing, interconnected network. Within the Virgo Supercluster, this network takes shape as a dense assembly of galaxies that seems almost endless, a literal sea of galaxies, each carrying billions of stars, gas clouds, planetary systems, and dark matter. Thinking about this sea can be both humbling and exhilarating because every point of light represents an entire universe in miniature, a city of stars moving through time and space. Observing the Virgo Supercluster reveals that the number of galaxies within it is staggering. Estimates suggest it contains over 1,000 significant galaxies, each a massive system of stars, and countless smaller dwarf galaxies that are faint but numerous. These smaller companions, though dim, are crucial in understanding the mass distribution, gravitational interactions, and history of the supercluster. Even though we cannot see all of them with the naked eye, each contributes to the structure, interacting with larger galaxies and forming streams, arcs, and bridges of stars and gas. The collective behaviour of these galaxies creates patterns that astronomers can measure and model, giving insight into the gravitational forces that shape the universe on an immense scale. The galaxies themselves vary widely. Spiral galaxies, with their graceful arms and ongoing star formation, coexist alongside massive elliptical galaxies that have long since exhausted much of their gas and now host older, cooler stars. Irregular galaxies add further diversity, often distorted by tidal interactions or past collisions. Observing this mix in the Virgo Supercluster allows astronomers to study how galaxies evolve in different environments. Dense regions, like the centre of the Virgo cluster, host a higher proportion of elliptical galaxies, while the outer regions retain more spirals and irregulars. This distribution reflects both the history of mergers and interactions and the influence of the supercluster's gravitational landscape. Despite their incredible numbers, the galaxies in Virgo are not randomly scattered. Gravity organises them into groups, clusters, and filaments, creating a structure that is intricate and highly ordered. Individual galaxies orbit within clusters, moving at hundreds or thousands of kilometers per second, subtly influencing one another through tidal forces. Over millions of years, these interactions shape their evolution, triggering star formation in some, stripping gas from others, and slowly reshaping their orbits and morphology. The galaxy streams and bridges we observe are evidence of this ongoing process, faint but revealing, telling a story of motion and interaction that spans millions of light years. The distances between galaxies in the Virgo supercluster can be difficult to comprehend. Even relatively close neighbours, on the scale of tens of millions of light years, are separated by vast expanses of space. Light from the nearest galaxies in the cluster takes millions of years to reach us, meaning when we observe them, we are seeing snapshots of events that occurred long before human history began. Each photon carries information about the motion, composition, and structure of a galaxy, allowing astronomers to map the distribution of galaxies, measure velocities, and understand the dynamics of the supercluster as a whole. These observations reveal patterns that are not immediately visible, but emerge through careful study, highlighting the complex yet coherent structure of the Virgo supercluster. Within this sea of galaxies, certain regions are particularly dense. The Virgo cluster itself serves as the supercluster's core. containing thousands of galaxies tightly packed together compared to the more sparse outer regions. Here, gravitational interactions are frequent, shaping galaxy morphology and evolution. Spiral galaxies often lose gas when passing close to massive neighbours, halting star formation and contributing to the growth of elliptical galaxies. Dwarf galaxies are especially vulnerable in these dense environments, often being tidally stripped or absorbed entirely. These processes demonstrate that the supercluster is not static, it is dynamic, a region of continuous motion and transformation where the fates of galaxies are intertwined. Astronomers use multiple techniques to study this sea of galaxies. Surveys that measure redshifts reveal how galaxies move relative to Earth, allowing scientists to determine which galaxies are gravitationally bound within the supercluster and which lie in the foreground or background. Observations across different wavelengths, including optical, infrared, and X-ray, provide complementary information about stars, gas, and hot plasma. Combining these data points creates a three-dimensional map of the supercluster, showing clusters, groups, and individual galaxies in space and time. This map not only illustrates the scale, but also the organization, revealing patterns in density, motion, and composition that define the Virgo supercluster. Beyond the visible stars, the intergalactic medium contributes to the structure of this sea. Hot, ionized gas permeates the space between galaxies, particularly in dense clusters. Though invisible to the naked eye, it emits X-rays detectable by specialized telescopes, adding another layer of complexity to the supercluster. This gas plays a critical role in galaxy evolution, supplying material for star formation, moderating interactions, and influencing gravitational dynamics. The presence of intergalactic gas emphasizes that a supercluster is more than just a collection of galaxies. It is an environment, a living system with multiple components interacting on a cosmic scale. The sheer number of galaxies also challenges our perception. Even if we could travel at the speed of light, moving from one edge of the Virgo supercluster to the other would take tens of millions of years. Each galaxy contains stars that have lifespans ranging from millions to billions of years. Planetary systems forming and evolving in parallel with their stars. When we consider this immense population, it becomes clear that the Virgo supercluster is not merely vast in space, but rich in history, with every galaxy representing countless cycles of birth, evolution, and sometimes quiet decay. Our own Milky Way, in comparison, is a single participant in a structure that contains thousands of galaxies, each with their own histories, interactions, and trajectories. It is also intriguing to consider how the galaxies within the supercluster interact gravitationally. Though separated by immense distances, their collective mass influences the motion of the local group and other nearby galaxy systems. Streams of galaxies move toward cluster centers, responding to gravitational wells created by both visible and dark matter. These motions, while imperceptible on human timescales, are measurable, allowing astronomers to calculate the mass and density distribution of the supercluster. Understanding these interactions reveals the underlying order within the apparent chaos, demonstrating that the sea of galaxies is not random, but shaped by predictable, measurable forces. Within this vast expanse, individual galaxies may seem insignificant, yet each plays a role in the overall structure. Interactions between galaxies create tidal tails, gas flows, and starbursts, influencing neighboring systems and contributing to the dynamic evolution of the cluster. Observing these phenomena provides insight into the life cycle of galaxies, showing that even minor components can have a significant effect over time. The cumulative influence of countless interactions over billions of years is what shapes the large-scale structure of the supercluster, highlighting the interplay between individual systems and the greater whole. Even as we consider the Virgo supercluster in terms of numbers and structure, there is a sense of coherence that emerges. Galaxies are not randomly scattered but follow patterns defined by gravity and cosmic history. central clusters are dense and active, surrounded by more diffuse outskirts, all linked through the invisible web of dark matter. These patterns demonstrate that the universe, even at its most enormous scales, exhibits order, predictability, and structure, inviting reflection on our place within it. As we continue to drift mentally through this sea of galaxies, it becomes apparent that the Virgo Supercluster is a dynamic, evolving environment. Galaxies are born, merge, interact, and die, and the supercluster itself grows and shifts over time. By observing the motions, distributions, and interactions of these countless systems, astronomers can trace the history of the structure, understand its dynamics, and even predict future evolution. This perspective allows us to appreciate not only the scale of the Virgo supercluster, but also its complexity and the forces that bind it together. Considering all of this, it is remarkable that the local group with the Milky Way at its centre is a small part of this immense sea. The motions we observe, the gravitational interactions, and the structural patterns all connect us to galaxies millions of light-years away. Light from the Virgo cluster itself takes over 50 million years to reach us, meaning that every observation is a glimpse into the distant past, a connection across time as well as space. This awareness brings both humility and wonder as we recognize that our galaxy participates in a vast, interrelated system that continues to evolve on scales far beyond human comprehension. At first glance, space can feel empty, a dark canvas punctuated by points of light, each representing stars or galaxies. Yet the reality is that distances between them are almost impossible to grasp. Within the Virgo supercluster, the vast stretches separating galaxies are measured in millions of light-years, units so large that they exceed ordinary comprehension, yet they are critical for understanding how galaxies move, interact, and influence one another. Even neighbouring clusters, though part of the same supercluster, are separated by regions of relative emptiness, where dark matter and intergalactic gas dominate the gravitational landscape. It is in these gaps that the supercluster's structure becomes apparent, with filaments connecting dense clusters and guiding the flow of galaxies through the cosmos. Considering the scale of these distances requires a mental shift. Light from the closest galaxies in the Virgo cluster takes approximately 50 million years to reach us. That is a measure not of physical separation alone, but also of time, as we observe these galaxies not as they are now, but as they were long before humans existed. This dual nature of distance, both spatial and temporal, adds complexity to our perception. When we observe the outer edges of the supercluster, light from some galaxies may have travelled over 100 million years, meaning every observation is a glimpse into deep cosmic history. These distances are not mere numbers. They represent the movement of matter over epochs that dwarf the entire history of life on Earth. Within the local group, distances between galaxies are comparatively small, on the order of hundreds of thousands to a few million light-years. Our nearest neighbour, the Andromeda Galaxy, lies about 2.5 million light-years away. Yet even this seemingly short distance is vast enough that light itself requires millions of years to bridge the gap. The Milky Way and Andromeda are moving toward each other, a slow gravitational convergence that will culminate in a merger billions of years from now. Observing this motion illustrates how distance in space is intimately tied to gravity and time. Even across the supercluster, galaxies are not static points, but moving entities, influenced by the collective mass of the clusters and the unseen scaffolding of dark matter. Mapping distances in a supercluster like Virgo involves precise measurement techniques. Astronomers use redshift, the stretching of light as objects move away due to cosmic expansion, to estimate distances over tens of millions of light-years. Cepheid variable stars, supernovae, and other standard candles provide additional tools, allowing observers to triangulate positions with surprising accuracy, given the immense scales. Combining these methods creates a three-dimensional map of the supercluster, revealing not only positions but velocities, orbital paths, and subtle gravitational influences. The result is a picture of space not as an empty void, but as a structured, interconnected environment where distances define interactions, evolution, and the very shape of the supercluster. Even within the Virgo cluster itself, galaxies are separated by millions of light years, yet gravity keeps them bound in a shared orbit around the cluster center. These orbital paths are not simple. They involve complex motions influenced by the mass distribution of the cluster, including dark matter halos that cannot be seen but whose effects are measurable. Smaller galaxies can be tugged along by larger companions, stretched into faint tidal streams or gradually absorbed into the central cluster. Observing these dynamics requires both spatial awareness and temporal understanding, as the distances involved translate directly into the time it takes for gravitational effects to propagate and for light to reach our instruments. Outside the dense central clusters, distances increase further. Galaxy groups and filaments stretch across tens of millions of light years, forming bridges and corridors that connect clusters within the supercluster. These filaments are often invisible to the naked eye but detectable through galaxy surveys and the gravitational lensing of background light. They guide the motion of galaxies, influencing where star formation occurs, how clusters evolve, and even how the supercluster as a whole maintains coherence. In this sense, distance is not simply separation. It is the medium through which gravity operates, a framework within which galaxies navigate the cosmic web. It is also intriguing to consider that even empty regions between galaxies are not truly void. These spaces contain diffuse gas, traces of dark matter, and occasional rogue stars or dwarf galaxies. While visually sparse, they contribute to the mass, gravity, and dynamics of the supercluster. Distances measured in light years are therefore not just abstract quantities. They represent regions filled with material and influence, shaping the evolution of galaxies and clusters across the supercluster. The emptiness between galaxies is relative, a vacuum by human standards, yet a medium for motion, interaction, and structure on an immense scale. Measuring distances in space also emphasizes the limitations of human perception. Unlike terrestrial distances, which can be directly observed and navigated, cosmic distances require indirect measurement and interpretation. When we say that the Virgo cluster is 50 million light-years away, we are describing both a spatial and temporal separation. The light we see began its journey long before the formation of the solar system, passing through a universe that has expanded and evolved during its transit. Every photon that reaches us carries information about a galaxy's past position, motion, and structure, effectively connecting us to a region of space and time far beyond our immediate experience. Considering the vastness of the Virgo supercluster, one begins to appreciate the significance of even seemingly small distances. A few million light-years may seem negligible on this scale, yet they determine whether galaxies interact directly, merge, or simply coexist in relative isolation. The motion of individual galaxies is influenced by the gravitational pull of others over these distances, and the trajectories traced by groups and clusters reflect cumulative effects across millions of years. In this sense, distance in space is both a measure of separation and a factor in cosmic causality, shaping the evolution of galaxies and the supercluster itself. The concept of distance also highlights the difference between observation and experience. While we can calculate the space between galaxies with precision, experiencing these distances is another matter entirely. Travelling even at the speed of a light, crossing the Virgo supercluster would require tens of millions of years. This reinforces the scale and grandeur of the structure, showing that even the nearest galaxies are staggeringly remote. Human experience operates on scales of hours, years, and centuries, yet the universe functions over spans that exceed comprehension. Distance becomes both a physical and philosophical concept, emphasizing our smallness and our capacity for wonder. Within the local group and extending outward, gravitational interactions also shape perceptions of distance. Galaxies that appear near each other in the sky may be separated by millions of light-years along the line of sight. Mapping their true three-dimensional positions requires careful measurement and consideration of redshift, velocity, and orientation. Observing these separations provides insight into the structure and formation of superclusters, revealing patterns that might otherwise be hidden. Distance is therefore not just a measure of space, but a key to understanding the history, evolution, and connectivity of the cosmos. As we contemplate these distances, it is also worth reflecting on the role of cosmic expansion. Space itself is stretching, meaning that galaxies are moving apart even without direct interactions. The supercluster remains gravitationally bound in its densest regions, yet on larger scales, the expansion of the universe subtly affects the separations between clusters and groups. Light travelling across these expanding distances is redshifted, providing astronomers with crucial information about the rate of expansion, the age of the universe, and the dynamics of cosmic structure. Distance, in this context, becomes a measure not only of separation but also of time, motion, and the changing geometry of space itself. Even within the Virgo Supercluster, the distances between galaxies create a sense of perspective. Central clusters are dense, yet outer regions stretch across tens of millions of light-years. Filaments connecting groups and clusters extend further, tracing the invisible threads of the cosmic web. Observing these separations emphasizes both the complexity and the coherence of the supercluster, showing that it is a living, evolving system with structure, motion, and history encoded in the distances between its members. Each galaxy's position is a clue to the forces at work, the past interactions that have shaped the cluster, and the future motions that will continue to evolve the system. Understanding distance in space helps us appreciate the scale and significance of our place within the supercluster. The Milky Way, part of the local group, occupies only a tiny fraction of the Virgo supercluster, yet it is influenced by the gravitational pull of the cluster as a whole. The distances that separate us from other galaxies are vast, but they are traversed by light, motion, and interaction, creating a web of connections that links our galaxy to countless others. Measuring, mapping, and contemplating these distances allows us to perceive the Virgo supercluster not as a collection of isolated points, but as an integrated system, vast yet comprehensible through patient observation and careful study. When you consider the vastness of the Virgo supercluster, it becomes clear that galaxies are not scattered randomly across space. Instead, they are part of a larger interconnected network known as the cosmic web, a framework of filaments, clusters, and voids that organizes matter on scales far beyond individual galaxies. These filaments are made primarily of dark matter, the invisible substance that dominates the universe's mass, guiding the formation and motion of galaxies along predetermined paths. Within this web, clusters and groups of galaxies act as nodes, where gravity pulls matter together, concentrating stars, gas, and dark matter in dense regions surrounded by vast, less populated voids. Understanding the cosmic web is essential to comprehending not only the Virgo supercluster, but also the underlying structure of the universe itself. The filaments of the cosmic web can be imagined as highways connecting dense clusters and groups, guiding galaxies through gravitational influence. These filaments are not empty corridors. They contain dark matter, gas, and occasional dwarf galaxies, all contributing to the overall mass and dynamics of the supercluster. The structure is hierarchical. Galaxies form groups, groups form clusters, clusters anchor the filaments, and the filaments themselves interconnect to create the supercluster. In the Virgo supercluster, this hierarchy is visible in both the distribution of galaxies and the motion of the local group, which drifts slowly along these filaments toward the central Virgo cluster under the influence of gravity. The web is dynamic, constantly evolving, yet structured in a way that reflects the underlying forces shaping the universe. Gravity is the primary architect of the cosmic web. While individual galaxies move according to local interactions, the large-scale flow of matter follows the gravitational contours of dark matter filaments. Observations of galaxy velocities reveal these flows, showing that galaxies are drawn along filaments toward dense nodes. Even though the distances are enormous, the motions are coherent, measurable, and consistent with models of gravitational dynamics. The cosmic web is thus both an organizing principle and a record of past motion, encoding information about how the universe has evolved over billions of years. Dark matter, though invisible, is fundamental to the web. It forms the scaffolding along which visible matter accumulates, guiding the formation of galaxies and clusters. Simulations of the universe show that without dark matter, the filamentary structure would not exist. Galaxies would remain isolated, clusters would be less massive, and superclusters like Virgo might not form in recognizable patterns. Observing the cosmic web allows astronomers to infer the distribution of dark matter, even when it cannot be seen directly, by mapping the positions, motions, and clustering of galaxies. In this way, the web provides insight not only into the architecture of superclusters, but also into the invisible forces that govern the universe. Within the Virgo Supercluster, filaments are visible in the distribution of galaxy groups and clusters. The central Virgo cluster acts as a gravitational anchor, drawing matter along multiple filaments that stretch tens of millions of light years. These filaments contain smaller clusters and groups, each moving along paths dictated by gravity, forming bridges between the dense center and more isolated regions. Observations of galaxy positions, redshifts, and velocities reveal this network, showing that the supercluster is not a uniform collection of galaxies, but a complex interconnected system, with matter flowing along defined channels and voids separating less populated regions. Void regions, though relatively empty, play a significant role in shaping the cosmic web. These areas of low density allow gravity to pull galaxies toward filaments and clusters, influencing their motion and the overall evolution of the supercluster. Voids are not entirely empty. They contain sparse gas and occasionally isolated galaxies, but their primary significance lies in providing the contrast that defines the web's structure. By studying the size, shape, and distribution of voids, astronomers gain insight into the forces that shape large-scale structures, the flow of matter across cosmic distances, and the formation history of superclusters like Virgo. The cosmic web also emphasizes the dynamic nature of the universe. Galaxies move along filaments, occasionally merging with others or being drawn into clusters. These motions occur over millions of years, imperceptible on human timescales, but significant in shaping the distribution of matter. Within filaments, galaxies interact weakly, maintaining relative isolation until they approach denser regions. In clusters, interactions are stronger, leading to mergers, star formation, or tidal stripping. The web is therefore both a map and a record of cosmic evolution, showing how matter flows, accumulates, and transforms across vast scales. Observing the cosmic web in practice requires advanced instruments and careful analysis. Large surveys, such as the Sloan Digital Sky Survey, map millions of galaxies to reveal their positions, velocities, and clustering patterns. These maps show the filamentary structure, highlight the nodes of dense clusters, and identify the voids that define the web. By combining data from different wavelengths, including optical, infrared, and X-ray, astronomers can trace galaxies, hot gas, and dark matter distributions. The resulting images of the cosmic web are both beautiful and informative, providing a visual representation of a structure that extends across hundreds of millions of light years. Even within a single filament, distances are immense. Galaxies can be separated by millions of light years, yet they remain connected by the gravitational influence of the filament and the surrounding dark matter. These connections guide motion, shape interactions, and influence the evolution of individual galaxies. The coherence of these structures is remarkable, considering the vast scales involved. Filaments act as pathways along which galaxies migrate, slowly funneling matter toward clusters and influencing the dynamics of superclusters like Virgo over billions of years. The concept of connectivity is central to understanding the cosmic web. Filaments do not merely connect clusters physically, they transmit gravitational influence, guide galaxy formation, and determine large-scale motion. The Milky Way, for instance, is subtly influenced by the gravitational pull of the Virgo cluster along the filament that links our local group to the supercluster. Even distant galaxies feel these forces, moving along paths dictated by the underlying mass distribution. Observing these motions reveals the structure of the web and helps astronomers understand the evolution of superclusters over cosmic time. Beyond gravity and dark matter, the cosmic web contains gas and plasma that fill the intergalactic medium. These components are essential for understanding galaxy formation and evolution. Gas within filaments can collapse to form new stars, feed galaxies, or create hot, ionized regions detectable in X-ray observations. The interaction between galaxies in this diffuse medium shapes star formation rates, galaxy morphology, and cluster dynamics. The web is therefore not only a framework of invisible matter, but also an environment in which galaxies grow, evolve, and interact, making it a living dynamic system rather than a static map. Considering the cosmic web in the Virgo supercluster also highlights the role of scale. Filaments stretch across tens of millions of light-years, connecting clusters separated by vast distances. Galaxies within these filaments move slowly, influenced by the cumulative gravitational pull of clusters, groups, and dark matter. Light travelling from these distant systems takes millions of years to reach us, providing snapshots of motion, structure, and evolution. Observing these connections allows astronomers to reconstruct the formation history of superclusters, understand the flow of matter, and model the dynamics of the universe at the larger scales. The web also emphasizes the interdependence of galaxies within a supercluster. Even seemingly isolated galaxies are part of a larger gravitational system, subtly influenced by neighboring galaxies' clusters and filaments. These forces shape motion, trigger interactions, and guide evolution over millions of years. The network is both hierarchical and interconnected, with small-scale effects cascading upward to influence larger structures. Understanding this interplay is essential for interpreting the motion, distribution, and evolution of galaxies in the Virgo supercluster. Contemplating the cosmic web invites reflection on our place within the universe. The Milky Way, the local group, and our neighbouring galaxies are all part of this vast network. The filaments that stretch through Virgo guide our motion, define the structure of the supercluster, and connect us to distant galaxies in a dynamic system spanning hundreds of millions of light-years. Observing the web, tracing its filaments, and understanding its nodes reveals not only the enormity of the universe but also the intricate order underlying it, offering a perspective that is both humbling and profoundly inspiring. When thinking about the Virgo supercluster, one of the first realizations is that its scale truly defies everyday understanding. Numbers like hundreds of millions of light-years do not come naturally to the human mind, yet they define the structure, reach, and influence of this immense cosmic neighborhood. To appreciate the size beyond imagination, it helps to compare it to more familiar distances, while keeping in mind that even these analogies barely capture the reality of a structure that stretches across such vast reaches of space. The Virgo supercluster contains dozens of galaxy groups, multiple clusters, and thousands of individual galaxies, all bound together by gravity, forming a three-dimensional shape that extends over approximately 110 million light-years. The Milky Way in this context is a small participant. Our galaxy, massive and complex as it is, spans about 100,000 light-years from edge to edge. Even the local group, which contains the Milky Way, Andromeda, Triangulum, and numerous dwarf galaxies, covers only a few million light-years. Comparing these scales to the full size of the Virgo supercluster highlights just how immense the structure is. hundreds of local groups, each containing dozens of galaxies, fit within the supercluster, with space and matter distributed along filaments, clusters, and less dense regions. The scale is both staggering and fundamental for understanding the motions, interactions, and evolution of galaxies within the supercluster. Light travels across these distances over millions of years, meaning that when we observe galaxies at the far reaches of Virgo, we are seeing them as they existed long before the first humans appeared on Earth. Even the nearest clusters in the supercluster require tens of millions of years for light to traverse, emphasizing that our observations are snapshots of events that unfolded in the distant past. The scale of time and space are intertwined. Size cannot be separated from the epochs over which galaxies move, interact, and evolve. Understanding this connection is critical when trying to grasp the enormity of the supercluster and the relative smallness of our own galaxy in comparison. Consider the Virgo cluster at the center of the supercluster, which alone contains thousands of galaxies concentrated in a dense core. The core measures several million light-years across, and surrounding it are galaxy groups and filaments that stretch tens of millions of light-years. Even within this dense region, distances between galaxies are immense, with stars and planetary systems effectively isolated in their respective galaxies. These separations illustrate the challenge of imagining the full scope of the supercluster. Each galaxy is a self-contained system, yet collectively they form part of an enormous network, a neighborhood so large that light itself takes millions of years to cross even a fraction of it. Expanding beyond the Virgo cluster, the supercluster stretches into surrounding filaments that connect smaller clusters and groups. These filaments form bridges across tens of millions of light years, guiding galaxies toward nodes of mass and contributing to the overall structure. Observations of galaxy distributions combined with redshift measurements reveal a three-dimensional network that emphasizes the true scale of the supercluster. Filaments not only link clusters, but also define regions of density and void, highlighting the vast stretches of space that are comparatively empty, yet integral to the overall architecture. To further illustrate the scale, imagine that if the Milky Way were reduced to the size of a grain of sand, the Virgo supercluster would span the size of an entire continent. Even dwarf galaxies, tiny by comparison, would be represented as pebbles scattered across this vast landscape. This analogy underscores the enormous distances and numbers involved, while also highlighting the fact that each galaxy, large or small, contributes to the gravitational field, motions, and evolution of the supercluster. The scale is difficult to internalize, yet it is essential for appreciating the structure, density, and dynamics of the region. The size of the Virgo supercluster also becomes apparent when considering its volume relative to the local group. The local group, spanning a few million light-years, is just one small node in the sprawling web of galaxies. Hundreds of similar groups fit within the Virgo supercluster, each moving under gravitational influence along filaments and toward cluster centers. Light from galaxies in the outer reaches of the supercluster has traveled for tens of millions of years before reaching us, emphasizing both the spatial and temporal vastness. Understanding this magnitude provides context for the motions of the Milky Way and other galaxies, situating our own cosmic neighborhood within a much larger system. Galaxies within Virgo move relative to each other at impressive speeds, often hundreds or thousands of kilometers per second. While these velocities are modest compared to the speed of light, they are significant over millions of years, causing shifts in position, interactions, and mergers. When multiplied across thousands of galaxies, these motions contribute to the evolution of the supercluster as a whole. The scale of movement, combined with the distances involved, creates a dynamic system that is constantly changing, even if the changes are imperceptible on human timescales. Observing the supercluster in its entirety reveals both the dense central regions and the more diffuse outskirts. The core, dominated by the Virgo cluster, is densely populated with galaxies, tightly packed and interacting frequently. Moving outward, galaxy groups become less dense, connected by filaments of dark matter and gas, eventually blending into the more isolated regions of the supercluster. The transitions from core to periphery illustrate the immense scale, showing that the supercluster is not a uniform entity, but a complex system with varying densities, compositions, and gravitational influences. Measuring the supercluster's size relies on a combination of techniques. Redshift surveys provide information about galaxy velocities and distances, allowing astronomers to map the three-dimensional structure. Observations of X-ray emission reveal the presence of hot gas within clusters, adding another measure of the scale and density. Gravitational lensing, the bending of light by mass, helps detect dark matter distributions, which are critical for understanding the overall size and shape. By integrating these methods, scientists can define the boundaries, nodes, and filaments of the supercluster, providing a clear, though still approximate, picture of its enormity. Even within the observed structure, there are faint galaxies and dwarf systems that are difficult to detect but contribute to the overall mass and dynamics. These smaller members, often invisible without sensitive instruments, are part of the gravitational framework that stabilizes clusters, maintains filaments, and guides motion. Considering their contribution highlights that the true size of the supercluster, in terms of mass and influence, may be even larger than observations suggest. The supercluster is thus not only enormous in physical dimensions, but also in the total matter it encompasses, both visible and invisible. Distances within the supercluster emphasize the challenges of scale. Galaxies that appear close in projection may be separated by millions of light-years along the line of sight. Mapping their positions accurately requires three-dimensional measurements, revealing a complex network of nodes, filaments, and voids. Even the local group with the Milky Way and Andromeda is just one small part of this vast network, influenced by the gravitational pull of distant clusters and guided along filaments that stretch across tens of millions of light-years. Understanding the size and distribution of these distances is essential for interpreting the structure, dynamics, and evolution of the supercluster. The enormity of the Virgo supercluster also emphasizes time on a cosmic scale. Light from the farthest members takes millions of years to reach us, providing a view into the distant past. Galaxies evolve, merge, and move along filaments over these timescales, and the supercluster itself changes, growing and restructuring under gravitational influence. Observing these changes allows astronomers to understand both the history and the future of the structure, highlighting that size is not simply a measure of space, but a measure of dynamic processes unfolding over unimaginable spans of time. Looking outward from our own vantage point, the Milky Way might seem enormous, a sprawling galaxy with hundreds of billions of stars, yet in the context of the Virgo supercluster, it is a relatively small participant, one node among countless others. Our galaxy resides within the local group, which itself is only one of many groups spread across the supercluster. Understanding our place in Virgo requires considering both position and motion, because the Milky Way is not stationary. It orbits the center of the local group, influenced by the gravitational pull of Andromeda and smaller companion galaxies, and the local group as a whole drifts slowly toward the Virgo cluster at the heart of the supercluster. These motions, though imperceptible in daily experience, define our trajectory across millions of light-years and connect us intimately to the larger cosmic structure. The local group consists of more than 50 galaxies, most of them dwarf systems, orbiting either the Milky Way or Andromeda. Triangulum, a smaller spiral, also plays a role, interacting gravitationally with its larger neighbours and influencing their dynamics over billions of years. Even these relatively close companions are separated by hundreds of thousands to millions of light-years, and their motions are part of the slow gravitational dance that extends outward to the Virgo cluster. When we place the local group within the Virgo supercluster, we begin to see that the Milky Way is a single point within a vast network of galaxies, influenced by nodes, filaments, and clusters spanning tens of millions of light years. Our position is neither central nor marginal. It is one among many, connected by invisible threads that guide motion and structure. The Milky Way's orbit within the local group is shaped largely by the mass distribution of Andromeda and other nearby galaxies. Over the next few billion years, the Milky Way and Andromeda are expected to merge, forming a new, larger galaxy. While this is a distant event, it emphasizes that even in our relatively small neighborhood, interactions define evolution. Within the Virgo Supercluster, similar processes occur on much larger scales. Galaxies are drawn along filaments, clusters grow by accreting smaller groups, and the local group itself moves toward denser regions, a motion dictated by the cumulative gravitational pull of millions of galaxies, dark matter, and intergalactic gas. Our trajectory toward the Virgo cluster is part of what astronomers call the local supercluster flow. Observations indicate that the local group is moving at roughly 1,100 km per second relative to the cosmic microwave background, drawn toward the gravitational center of Virgo. This motion, slow in human terms but significant across cosmic distances, means that our galaxy, along with the other members of the local group, will eventually approach the Virgo cluster, though the journey will take tens of millions of years. This movement highlights that our place in Virgo is dynamic. The Milky Way is not a static observer, but an active participant in the gravitational network that defines the supercluster. Considering our location also emphasizes the relative isolation within the local group. While clusters contain thousands of galaxies packed into a few million light-years, our group is comparatively sparse, allowing the Milky Way and Andromeda to evolve largely undisturbed, except for interactions with smaller satellites. This relative calm is part of what makes our galaxy habitable and stable over billions of years. In contrast, galaxies at the center of the Virgo cluster experience constant interactions, mergers, and gravitational perturbations, illustrating how position within the supercluster affects evolution, environment, and dynamics. Satellite galaxies around the Milky Way provide additional insight into our place in Virgo. The large and small Magellanic Clouds, for example, are dwarf galaxies orbiting our system, contributing to star formation, tidal streams, and gravitational interactions. These satellites reflect the hierarchical structure of the universe on a small scale. Galaxies orbiting larger systems, which in turn move through groups, clusters, and superclusters. Observing these interactions offers a microcosm of the larger patterns that define Virgo, showing that the same physical laws apply across scales from hundreds of thousands to millions of light years. The local group is positioned at the edge of the Virgo supercluster rather than its dense core, giving us a perspective that is both distant and connected. From this vantage point, we can observe the Virgo cluster, the supercluster's central node, as a dense collection of galaxies influencing our motion. Filaments of dark matter connect us to the cluster, guiding the drift of the local group. This position at the periphery provides a unique perspective, allowing astronomers to study the structure, motion, and evolution of Virgo from a relatively isolated location, observing the supercluster without being overwhelmed by the extreme density at its center. Our location also affects how we perceive motion on larger scales. The local group moving toward Virgo is part of a broader pattern that includes other groups and clusters moving in similar directions. This collective motion is a result of gravitational attraction within the supercluster, influenced by the mass of the Virgo cluster and surrounding filaments. Observing this flow allows astronomers to map the supercluster, measure its mass, and understand the dynamics that govern galaxy motions. In this way, our position is both subject and tool. We are influenced by the supercluster, yet our observations help define its structure. Distances from other parts of the supercluster reinforce our smallness in scale. While we orbit within the local group, the nearest massive cluster in Virgo is about 50 million light-years away. Galaxies at the outer edges of the supercluster can be more than 100 million light-years distant. These separations mean that interactions with the core cluster are slow, and the Milky Way is relatively isolated compared to galaxies in denser environments. Yet gravity ensures that no galaxy is entirely independent, and over millions of years, motion, attraction, and collision continue to shape the structure of the supercluster. Mapping our place in Virgo also highlights the interconnectedness of all components. Filaments guide galaxy motion, clusters influence group dynamics, and the local group is part of a coherent gravitational network. The Milky Way, while small relative to the supercluster, participates in the same forces and structures, moving along pathways defined by both visible and invisible matter. Understanding this interconnectedness reveals that our position is not random. It is the result of billions of years of motion, formation, and gravitational influence, situating the Milky Way within a vast and evolving cosmic environment. Even as we recognize the enormity of the supercluster, it is worth noting that the local group's location provides observational advantages. Being relatively distant from the dense Virgo cluster allows us to study the structure, motions, and composition of the supercluster without interference from extreme densities. Our peripheral position enables astronomers to trace filaments, map galaxy distributions, and measure velocities, providing a comprehensive view of Virgo's structure. The Milky Way thus acts as a vantage point, offering a perspective that combines proximity and separation, intimacy and distance, allowing us to explore the supercluster both scientifically and contemplatively. In addition to motion and structure, our position affects the gravitational environment of the Milky Way. While clusters in the center of Virgo experience strong tidal forces and frequent interactions, our local group enjoys relative stability. This calm has implications for star formation, planetary system stability, and the overall evolution of galaxies within our neighborhood. The dynamics of the local group combined with its location in the supercluster illustrate how position within Virgo determines not only motion, but also the potential for long-term development and change. Considering these factors together, our place in Virgo can be seen as a balance between isolation and connection. We are distant enough from the dense cluster core to avoid extreme interactions, yet connected through filaments and gravitational influence. Our motion toward the Virgo cluster is slow but persistent, part of the ongoing evolution of the supercluster. Satellite galaxies, local group neighbors, and filaments all contribute to our environment, creating a network of forces, motion, and structure that define our location. From this perspective, it becomes clear that the Milky Way is both small and significant. Small in comparison to the enormous scale of Virgo, yet significant as part of the local group and as an observer of the supercluster. Our location allows us to understand the dynamics of nearby clusters, trace the motion of galaxies, and participate indirectly in the larger cosmic web. Recognizing this duality, being small within an immense system yet able to observe and comprehend that system, highlights the wonder of our place in the universe. Observing the Virgo supercluster in detail, it becomes clear that it is not a uniform expanse of galaxies, but a structure layered with complexity, where clusters exist within clusters, each bound together by gravity yet distinct in size, density, and composition. At the heart of the supercluster lies the Virgo cluster itself, a dense collection of thousands of galaxies whose combined mass dominates the motion of surrounding groups. Within this central cluster, smaller subclusters form, each a localized concentration of galaxies orbiting a shared center of gravity. These substructures are essential for understanding how the supercluster functions, revealing a hierarchy of organization that extends across millions of light years. Even as we trace the contours of the Virgo cluster, it becomes apparent that the galaxies within are not randomly arranged. They are grouped into smaller clusters, often dominated by massive elliptical galaxies at the core. These central galaxies exert gravitational influence over surrounding members, shaping orbital patterns, merging smaller companions, and occasionally triggering bursts of star formation in nearby spirals. The subclusters within Virgo illustrate the dynamic nature of superclusters, showing how gravitational forces operate on multiple scales simultaneously, from the smallest dwarf galaxies to massive central ellipticals, all contributing to the overall structure. Examining the density of these clusters highlights their significance. In the central regions, galaxies are packed closely together, separated by distances measured in hundreds of thousands of light-years rather than millions. In these dense environments, interactions occur frequently. Tidal forces stretch galaxies, mergers create new structures, and intergalactic gas is redistributed. These processes demonstrate that clusters within clusters are active environments, where the motions and properties of individual galaxies are constantly evolving. Even galaxies on the periphery of subclusters feel subtle influences, slowly pulled toward a denser cause over millions of years. The hierarchical nature of clusters within the Virgo supercluster also reveals itself in velocity patterns. Galaxies within a subcluster orbit their common center of mass, while the subcluster as a whole moves within the larger cluster. These motions, though slow by human standards, are measurable with precise instruments. Redshift measurements and observations of galaxy dynamics show how subclusters move relative to each other, providing insight into the mass distribution of the supercluster and the gravitational forces at play. Observing these velocities allows astronomers to trace the flow of matter, identify gravitational wells, and understand the long-term evolution of the system. Even smaller groupings exist within the subclusters. Dwarf galaxies, sometimes numbering in the hundreds, orbit larger members, contributing to streams of stars, tidal tails, and faint halos. These tiny galaxies, though individually insignificant in mass, collectively influence the gravitational landscape, providing additional mass and shaping the motion of larger neighbours. Their presence also allows astronomers to study the formation and evolution of galaxies on smaller scales, offering a glimpse into the processes that govern both local and large-scale structure within the supercluster. The composition of clusters within clusters varies. Central subclusters often contain large elliptical galaxies with little ongoing star formation, while spirals are more common on the outskirts. Irregular galaxies and interacting systems add diversity, sometimes forming bridges and streams between members. These variations illustrate that density, environment, and gravitational history shape galaxy evolution within clusters. Observing the distribution of galaxy types within the Virgo cluster helps astronomers understand how interactions, mergers, and environmental effects influence morphology, star formation, and the long-term growth of galaxies. Distance between subclusters within Virgo is another factor that defines structure. While galaxies within a subcluster may be separated by hundreds of thousands of light-years, neighbouring subclusters are often millions of light-years apart. These separations are bridged by gravity, which slowly draws clusters together over cosmic time. Filaments of dark matter connect subclusters, guiding motion and creating pathways along which galaxies and groups migrate. These filaments also channel gas, providing material for star formation and influencing the dynamics of both individual galaxies and clusters. The distances between subclusters, combined with their interactions, create a layered three-dimensional structure that is both intricate and dynamic. Mass distribution within these nested clusters is uneven. The central galaxies, often ellipticals, dominate the gravitational influence, while surrounding spirals and dwarfs contribute smaller amounts of mass. Yet when considered collectively, the subclusters contain enough mass to influence the motion of the entire Virgo cluster. Dark matter, pervasive yet invisible, forms halos around clusters and filaments, shaping orbits and anchoring galaxies within the supercluster. Observing these effects allows astronomers to estimate the total mass of the system, revealing that much of the supercluster's mass is hidden, yet critical for understanding motion, structure, and evolution. Interactions between clusters and subclusters are ongoing. Occasionally, smaller clusters are drawn toward the central Virgo cluster, merging over millions of years. These mergers can trigger star formation, redistribute gas, and reshape orbits, creating temporary turbulence that eventually settles into a new equilibrium. Observing these processes provides insight into the dynamic evolution of superclusters, showing that even on the larger scales, change is constant, subtle, and profoundly influential. Clusters within clusters are therefore not isolated. They interact, grow, and evolve as part of a coherent system, illustrating the hierarchy and interconnectedness that define the Virgo supercluster. Studying these nested structures also allows astronomers to test theories of cosmology. By mapping subclusters, measuring velocities, and tracing interactions, scientists can compare observations with simulations, verifying models of dark matter distribution, gravitational dynamics, and large-scale structure formation. The Virgo supercluster serves as a laboratory for understanding the processes that shape the universe, showing how matter organizes from small groups to massive clusters and ultimately into sprawling superclusters. Each nested cluster provides a piece of the puzzle, revealing the mechanisms by which galaxies accumulate, interact, and move across cosmic time. Even within a single subcluster, dynamics are complex. Galaxies follow elliptical orbits, influenced not only by the central mass, but also by neighbouring galaxies, intergalactic gas, and dark matter. Tidal forces create streams and distortions, while mergers can dramatically alter structure and star formation. These interactions, though imperceptible on short timescales, accumulate over millions of years, producing the varied morphology observed within the cluster. Observing these processes offers insight into the evolution of galaxies in dense environments, highlighting the role of proximity, gravity, and mass in shaping the history of the supercluster. The hierarchical nature of the Virgo supercluster also extends to gas distribution. Intergalactic gas is more concentrated within dense subclusters, contributing to X-ray emission detectable by telescopes. This gas interacts with galaxies, stripping material from spirals and fueling star formation in others. Hot plasma fills the spaces between galaxies, adding mass and influencing gravitational interactions. These gaseous components, combined with dark matter and stars, define the physical and gravitational environment of each cluster and subcluster, emphasizing that the supercluster is a complex multi-component system rather than a simple collection of galaxies. Even seemingly isolated galaxies within Virgo are affected by clusters and subclusters. Their motions, interactions, and evolution are influenced by nearby density peaks, gravitational potential wells, and filaments that connect nodes of matter. Observing these effects provides insight into the long-range influence of clusters, showing that even distant galaxies are linked to the central structure. The hierarchy of clusters within clusters ensures that motion, structure, and evolution are interconnected, producing coherent patterns across the supercluster. Understanding clusters within clusters also allows us to trace the history of formation. Observations of galaxy density, types, and motion reveal past mergers, accretion events, and tidal interactions. Subclusters often contain remnants of smaller systems absorbed over billions of years, and streams of stars and gas trace the path of these interactions. By studying these structures, astronomers can reconstruct the evolution of the Virgo supercluster, gaining insight into the processes that have shaped galaxies, clusters, and the overall architecture of the region. Nothing defines the Virgo supercluster more fundamentally than mass and gravity, because they are the forces that hold together this enormous collection of galaxies, clusters, and filaments. The supercluster may appear as a loose association of thousands of galaxies, but it is gravity, both visible and invisible, that gives structure and cohesion. Without this force, the galaxies would drift apart with the expansion of the universe, dispersing into emptiness, leaving no coherent supercluster behind. Every motion, every orbit, every filament connecting clusters is shaped by gravitational influence, and the total mass of the system, both observed and hidden, dictates how it evolves over cosmic time. The Virgo Supercluster contains an extraordinary amount of mass, but much of it is not in the form of stars or visible matter. Dark matter dominates, forming halos around clusters and subclusters, extending far beyond the luminous regions of galaxies. This unseen mass provides the gravitational scaffolding that binds the supercluster, guiding the motions of galaxies along filaments and maintaining the coherence of clusters within clusters. Observations of galaxy velocities reveal that the visible matter alone is insufficient to account for the motion we measure. The majority of the supercluster's mass is invisible, yet it exerts influence on every member galaxy, including the Milky Way. Even within individual clusters, mass is unevenly distributed. Central elliptical galaxies often dominate the gravitational pull, while surrounding spirals and dwarf galaxies contribute smaller amounts. The cumulative effect, however, is immense. Clusters act as nodes within the supercluster, their combined gravity drawing in nearby groups, influencing the local group, and shaping the flow of galaxies along connecting filaments. Gravity operates on scales both vast and subtle, orchestrating motion across tens of millions of light-years, while simultaneously influencing the internal dynamics of individual galaxies and clusters. Measuring the mass of the supercluster relies on careful observation of galaxy motions, gravitational lensing, and the distribution of gas and dark matter. Redshift surveys provide velocities, allowing astronomers to infer gravitational influence, while X-ray observations of hot intergalactic gas reveal the depth of potential wells within clusters. Gravitational lensing, the bending of light from background galaxies, maps the distribution of dark matter, providing another crucial clue to total mass. These measurements show that the Virgo supercluster contains hundreds of times more mass than what is visible in stars and galaxies alone, emphasizing the critical role of dark matter in holding the structure together. The influence of gravity extends across the supercluster. Galaxies are not static. They move along paths determined by the combined gravitational forces of clusters, filaments, and dark matter. Even relatively isolated galaxies are subject to these forces, which over millions of years guide motion toward denser regions or along filaments connecting nodes of mass. Observing these motions allows astronomers to model the dynamics of the supercluster, tracing how matter flows, how clusters evolve, and how the gravitational influence of central nodes like the Virgo cluster shapes the environment. Within individual clusters, tidal forces created by massive central galaxies influence neighbouring members. Spirals can be stretched or distorted, dwarf galaxies can be pulled apart, and streams of stars are created from these interactions. These tidal effects demonstrate that gravity operates not only on large scales across the supercluster, but also on smaller scales within clusters, creating a complex network of forces that govern both motion and evolution. Every galaxy, no matter how small, participates in this gravitational hierarchy, moving in response to both local and large-scale forces. The supercluster's mass also affects the local group. Our galaxy, orbiting within the local group, experiences the combined gravitational pull of Virgo and its constituent clusters. This influence guides our trajectory, contributing to the motion toward the Virgo cluster at roughly 1,100 kilometers per second relative to the cosmic microwave background. Over millions of years, this pull shapes our orbit within the local group and the path of the local group itself, linking us to the dynamics of the supercluster. Without this gravitational influence, our galaxy's trajectory would be different, and the larger structure of the supercluster would not function in the organized way we observe. Gravity also organizes the filaments that connect clusters and groups within the supercluster. These filaments, composed of dark matter, gas, and galaxies, act as channels along which matter flows, guided by the gravitational potential of massive nodes. Galaxies move along these filaments toward denser regions, tracing the paths dictated by gravity. Over cosmic time, this motion contributes to the growth of clusters and subclusters, maintaining the coherence of the supercluster. Observing these flows allows astronomers to understand how mass and gravity combine to shape large-scale structure, illustrating that the supercluster is not static but a dynamic system evolving under the influence of gravity. The distribution of mass within Virgo also explains the relative motions of individual galaxies. Central clusters with high mass concentrations exert stronger gravitational pull, causing peripheral galaxies and subclusters to move toward the core. These motions are measurable and predictable, reflecting the cumulative effect of gravity over millions of years. Even galaxies at the outer edges of the supercluster feel this influence, moving slowly along filaments, responding to the gravitational landscape shaped by visible and invisible matter. The interconnected nature of mass and gravity ensures that motion, position, and evolution are linked across all scales. Observing the supercluster in this context emphasizes both scale and complexity. Gravity operates continuously, connecting galaxies across millions of light years, influencing the orbits of stars, the paths of satellite galaxies, and the motion of entire clusters. The Milky Way is just one participant in this vast system, subtly affected by the gravitational pull of distant clusters and filaments. Yet this same gravity allows the supercluster to maintain coherence, despite the vast distances and immense number of galaxies involved. Without these forces, the structure would disperse, and the intricate patterns we observe in Virgo would not exist. The cumulative mass of Virgo also affects the evolution of the galaxies within it. In dense regions, gravity increases the frequency of interactions, mergers, and tidal effects. Gas is funneled into central galaxies, fueling star formation or feeding supermassive black holes. In less dense regions, galaxies retain more of their gas, continuing star formation independently. These variations illustrate how mass and gravity not only shape motion, but also influence the internal evolution of galaxies, demonstrating that the supercluster structure is closely tied to the distribution and magnitude of its mass. Even the smallest components contribute to the gravitational framework. Dwarf galaxies, satellite systems, and diffuse gas add mass that, while individually small, collectively influences the dynamics of clusters and filaments. Streams of stars and tidal debris, often the remnants of past interactions, trace the pathways along which gravitational forces operate. Observing these features allows astronomers to reconstruct the mass distribution and gravitational interactions within the supercluster, providing a deeper understanding of how structure and motion are maintained across such vast scales. Mass and gravity are also essential for understanding the cosmic web that underpins Virgo. Filaments are held in place by dark matter, guiding galaxies toward clusters and shaping the large-scale topology of the supercluster. Gravity ensures that these structures remain coherent over billions of years, allowing matter to flow along predictable paths while maintaining connections between clusters, subclusters, and isolated galaxies. Observing the effects of gravity across this network provides insight into the evolution of the universe on the larger scales, showing that the supercluster is both a product of and a participant in the forces that govern cosmic structure. Considering these factors together, it becomes clear that mass and gravity define every aspect of the Virgo supercluster. They determine how galaxies move, how clusters interact, how filaments form, and how the supercluster evolves over cosmic time. The Milky Way, orbiting within the local group, is part of this intricate system, influenced by forces that extend across tens of millions of light years. Understanding mass and gravity is therefore essential, not only for mapping the supercluster, but also for appreciating our place within it, as participants in a vast gravitational network that shapes every motion and every structure within Virgo. Even within the immense structure of the Virgo supercluster, galaxies are not stationary. Each galaxy traces a path dictated by the combined gravitational forces of its neighbours, the clusters it belongs to, and the filaments that connect it to the wider cosmic web. Observing these motions is akin to watching a carefully choreographed dance, except that the performers are billions of stars moving through hundreds of thousands of light years. and the rhythm is set by gravity over millions or even billions of years. The Milky Way itself is part of this dance, orbiting within the local group while the entire group moves toward the Virgo cluster, tracing a path influenced by the enormous mass of the supercluster. In the densest regions, such as the central Virgo cluster, the motions of galaxies are particularly complex. Elliptical galaxies, often massive and ancient, move in smooth elliptical orbits around the cluster's centre, their paths shaped by the combined gravitational influence of surrounding galaxies and dark matter halos. Spiral galaxies, slightly less massive but still significant, orbit along less predictable trajectories, sometimes interacting with neighbours, forming tidal streams, or colliding gently with smaller galaxies. Even within a single cluster, the motions are layered, with each galaxy responding to the forces of others while maintaining its own trajectory, creating a dynamic interconnected system. Galaxies and subclusters exhibit similar patterns, moving around common centres of mass while subtly influencing and being influenced by nearby groups. Dwarf galaxies, though small in comparison, play a role in these dances as well. Their orbits can be altered by larger neighbours, stretched into streams, or even absorbed entirely, contributing stars and gas to the larger system. Over time, these interactions shape the morphology, composition, and distribution of galaxies within clusters, demonstrating that motion is not random but a product of gravitational interactions and environmental effects. The cosmic filaments that connect clusters and subclusters act as guiding pathways for galaxies. Matter flows along these filaments toward dense nodes, influencing trajectories even far from the cluster core. Galaxies moving along filaments follow curved paths dictated by the gravitational landscape, sometimes merging with other groups or gradually spiraling toward cluster centers. Observing this motion allows astronomers to map the gravitational influence of the supercluster, revealing how the distribution of mass shapes the flow of matter across millions of light years. These motions are slow in human terms but continuous, producing a dynamic system that evolves over cosmic time. Even seemingly isolated galaxies participate in this dance. Though they may appear far from clusters or groups, they are still influenced by the gravitational pull of filaments and more massive structures nearby. Over millions of years, these subtle forces can alter their orbits, bring them closer to clusters, or reshape their trajectories entirely. In this sense, every galaxy in the Virgo supercluster is interconnected, its motion a reflection of both local interactions and large-scale gravitational patterns. The dance is universal, linking every member of the supercluster in a slow, deliberate choreography. Observing these motions requires sophisticated techniques. Redshift measurements provide velocity data, showing how galaxies move toward or away from us, while proper motion studies reveal lateral movement across the sky. Combined, these measurements allow astronomers to reconstruct the three-dimensional trajectories of galaxies, revealing both local orbital paths and large-scale flows. These observations demonstrate that galaxies within Virgo are not static points, but active participants in a continuous gravitationally driven dance, each motion influenced by mass, position, and history. The dynamics of galaxy interactions are also evident in collisions and mergers. When galaxies pass close to one another, tidal forces stretch and distort their structures, forming streams of stars and gas that trace the path of gravitational influence. Sometimes these encounters trigger bursts of star formation, lighting up regions with brilliant new stars. Over longer timescales, repeated interactions can result in mergers, combining two or more galaxies into a single, more massive system. Within the Virgo supercluster, these processes occur frequently in dense regions and occasionally in the outskirts, shaping the evolution of galaxies across the supercluster. Even on the outskirts of clusters, the dance continues. Galaxies in more diffuse regions move along filaments, often in pairs or small groups, gradually converging toward denser nodes. Their motion is guided by the combined gravitational pull of clusters, filaments, and nearby groups, producing curved paths that can take millions of years to complete. Observing these flows provides insight into the structure of the supercluster, the location of mass concentrations, and the paths along which galaxies migrate, demonstrating that the dance is not confined to the center, but occurs across the entire system. The interaction of multiple gravitational influences creates a layered effect in galaxy motion. A single galaxy may orbit a cluster center, while simultaneously being pulled along a filament toward a denser node. Neighboring galaxies exert additional forces, creating local distortions in orbit, while dark matter halos provide an invisible framework that shapes overall motion. This complexity produces a variety of orbital paths, velocities, and interactions, illustrating that the dance is intricate, multi-dimensional, and governed by both visible and invisible mass. Even individual stars within galaxies participate indirectly in this motion. As galaxies orbit, collide, or interact, the stars within them follow the gravitational paths dictated by their host galaxy's dynamics. Tidal interactions can redistribute stars, creating streams that extend across tens of thousands of light years. Star formation may be triggered by collisions or gas compression, altering the internal structure of the galaxy while contributing to the overall evolution of the supercluster. In this way, the dance of galaxies directly influences the evolution of individual systems, demonstrating the cascading effects of gravity across scales. The dance is continuous and cumulative. Every orbit, every interaction, every motion contributes to the evolution of the Virgo Supercluster. Subclusters merge, filaments guide flow, clusters grow, and galaxies change shape and composition. This continuous movement maintains the coherence of the supercluster, ensures the flow of matter along defined paths, and allows the system to evolve in a predictable, measurable way. Observing these dynamics provides both perspective and understanding, revealing the active nature of structures that might otherwise seem static when viewed in a single snapshot. Even our local group participates in this choreography. The Milky Way orbits the center of mass of the local group, while the entire group drifts toward the Virgo cluster. The motion is slow, stretching across millions of years, but measurable and consistent with the gravitational influence of the surrounding supercluster. Satellite galaxies orbit our galaxy, streams of stars trace past interactions, and the entire system moves as a cohesive participant within the larger dance of the supercluster. Our place is therefore active, not passive, connected to the dynamics of distant galaxies and clusters through gravitational influence. Observing the dance of galaxies also emphasizes the role of time. Light from galaxies in the Virgo supercluster takes tens of millions of years to reach us, meaning that the motions we perceive are echoes of the past. Every orbit, every merger, and every tidal interaction unfolded long before humans could observe them, yet we're able to reconstruct these paths using careful measurement, simulation, and observation. The dance exists over both space and time, and our understanding of it requires combining the positions, velocities, and interactions of galaxies to perceive patterns that span millions of years and millions of light years. Even in the less dense regions of the supercluster, galaxies follow similar principles. Groups along filaments move toward denser nodes, interact with neighbors, and gradually contribute to cluster growth. These motions are slower and less dramatic than in the core regions, but they are no less significant. Over cosmic timescales, these gradual movements accumulate, creating changes in the distribution of matter, the alignment of clusters, and the overall evolution of the supercluster. The dance is therefore universal, connecting core and periphery in a continuous, coordinated pattern. Gravity also regulates the speed of this dance. Galaxies in dense clusters move faster due to the stronger gravitational pull, while those in the outskirts drift more slowly along filaments. This variation produces a range of orbital speeds from hundreds to thousands of kilometers per second, creating a dynamic environment where interactions occur more frequently in dense regions and less often in sparse areas. Observing these speeds allows astronomers to infer mass distribution, predict future motion, and understand the energy within the supercluster. Even with all this complexity, there is order in the dance. Galaxies follow predictable paths dictated by gravity, and clusters remain coherent over billions of years. Filaments guide flow, interactions shape evolution, and subclusters maintain their identity while contributing to the larger structure. The supercluster is a dynamic but organized system, where motion, mass, and distance interact to produce the continuous, intricate dance of galaxies that defines Virgo. Finally, considering the motions of galaxies in this way emphasizes both scale and connectivity. The Milky Way, part of the local group, participates in this slow, persistent movement, influenced by nearby galaxies, subclusters, and the Virgo cluster itself. Looking beyond the stars, we can see the Virgo supercluster is dominated by elements that are invisible to our eyes yet fundamental to its structure. Most of the supercluster's mass is not found in galaxies or interstellar gas, but in dark matter, an unseen substance that forms the gravitational scaffolding for the entire region. Dark matter does not emit, absorb, or reflect light, yet its presence can be inferred from its effects on galaxies, clusters, and the motion of the supercluster itself. Without this invisible component, the galaxies of Virgo would not orbit as they do, the filaments of the cosmic web would not hold, and the intricate dance of galaxies would unravel, leaving behind a far less coherent system. Observations of galaxy motion within clusters make the influence of dark matter evident. Galaxies move faster than their visible mass alone would allow, indicating that an unseen force is exerting gravitational pull. This discrepancy led astronomers to conclude that dark matter must comprise a substantial portion of the mass in the Virgo supercluster. Surrounding the Virgo cluster, halos of dark matter envelop individual galaxies, subclusters, and the filaments connecting them. These halos are invisible, yet they define the structure, dictating paths of motion, orbiting patterns, and the overall dynamics of the supercluster. In addition to dark matter, intergalactic gas plays a critical role. A hot, ionized gas fills the spaces between galaxies, particularly within dense clusters. This gas is not visible without specialized instruments, yet it contributes significant mass, emits X-rays, and interacts with galaxies through gravitational and hydrodynamic effects. In some cases, the gas can strip material from galaxies as they move through clusters, halting star formation and altering morphology. These invisible components demonstrate that what we see, galaxies and stars, is only a fraction of the total matter shaping the supercluster, with most mass hidden yet dynamically essential. Even in the filaments that connect clusters, dark matter and gas dominate. Galaxies travelling along these filaments are guided by the gravitational pull of unseen mass, following paths that reflect both the distribution of dark matter and the flows of intergalactic gas. These filaments act as conduits, guiding matter toward dense nodes and maintaining the coherence of the supercluster. Observations of gravitational lensing, redshift surveys, and X-ray emission reveal these structures, allowing astronomers to map the invisible framework and understand how galaxies move, interact, and evolve within it. The Milky Way, within the local group, is indirectly affected by these invisible components. The combined gravitational influence of dark matter within the local group, nearby filaments, and the Virgo cluster itself shapes our motion, guiding the local group toward the supercluster's central regions. Even though we cannot see these forces, their effects are measurable, detectable in the velocities, orbits, and trajectories of galaxies. This demonstrates that the invisible components are not merely background features, but active participants in the dynamics of the supercluster. Hot gas within clusters contributes not only mass but energy. Moving galaxies interact with this gas through ram pressure stripping, collisions, and tidal interactions. Gas can be compressed, triggering star formation in some galaxies while removing material from others. Observing these processes requires sensitive instruments such as X-ray telescopes, which reveal the presence, temperature, and density of the gas. These observations provide a more complete picture of the supercluster, showing that visible matter is just one layer of a complex interconnected system in which dark matter, gas, and stars interact. Dark matter also determines the shape of clusters and subclusters. Halos of dark matter provide the gravitational potential wells around which galaxies orbit, maintaining cluster cohesion and influencing orbital velocities. Without these invisible structures, clusters would be less dense, galaxies would drift apart, and the supercluster would lack the organization necessary to maintain its current form. The combined effects of dark matter halos and intergalactic gas produce a gravitational framework that is stable yet dynamic, guiding galaxies through predictable paths while allowing interactions, mergers, and evolution. Even faint dwarf galaxies within clusters are influenced by invisible components. Their orbits are shaped by the gravitational pull of larger galaxies and dark matter halos, while intergalactic gas affects star formation and gas retention. Streams of stars and gas created by tidal interactions trace the influence of gravity over millions of years, providing observable evidence of otherwise unseen forces. These small galaxies, though individually minor in mass, collectively contribute to the dynamics of the supercluster, reinforcing the role of invisible components in shaping large-scale structure. The cosmic web, supported by dark matter and gas, provides additional insight into the supercluster's invisible architecture. Filaments connect clusters and subclusters, channeling galaxies along gravitational pathways. The density of dark matter within these filaments determines the speed and direction of motion, while intergalactic gas adds friction and mass, influencing the evolution of galaxies as they travel. This network is essential for maintaining coherence across the supercluster, ensuring that clusters remain connected and matter flows predictably along established paths. Mapping invisible components requires careful observation and advanced techniques. Gravitational lensing reveals the distribution of dark matter by bending the light of distant galaxies. X-ray and radio observations detect hot gas in clusters and filaments, providing measures of density, temperature, and composition. Combining these data allows astronomers to construct detailed models of the supercluster, illustrating how visible and invisible matter interact. Without these measurements, the Virgo Supercluster would appear as a collection of galaxies with no clear structure. Yet these invisible components provide the framework that organizes the entire system. The influence of invisible components extends across scale. From small dwarf galaxies to massive clusters, all are subject to the gravitational pull of dark matter. Interactions with intergalactic gas shape star formation, morphology, and motion. Even isolated galaxies feel the combined effects of distant mass concentrations, moving along filaments and responding to gravitational potential wells. Observing these interactions highlights the interconnectedness of the supercluster, showing that invisible components govern both local dynamics and large-scale structure. Time also amplifies the importance of invisible components. Over millions of years, the motion of galaxies, the flow of gas, and the influence of dark matter accumulate, shaping the structure, evolution, and cohesion of the supercluster. Small effects compound over time, guiding the drift of galaxies, the merging of clusters, and the gradual reshaping of filaments. The invisible components, though imperceptible in a single moment, are therefore central to the ongoing development of Virgo, quietly orchestrating the motions that define the cosmic landscape. Even our local group is affected in subtle ways. Dark matter halos of nearby clusters exert gravitational influence on our galaxy, while filaments guide the motion of the local group toward the Virgo cluster. The intergalactic medium, while sparse, contributes to the gravitational environment and the evolution of satellite galaxies. These forces, though imperceptible to the eye, shape the path of the Milky Way, situating it within the supercluster and connecting it to galaxies millions of light-years away. the combination of visible and invisible components creates a dynamic equilibrium. Gravity from dark matter and clusters guides motion. Intergalactic gas influences evolution, and galaxies interact with one another, producing streams, mergers, and structural change. This equilibrium maintains the coherence of the supercluster while allowing it to evolve over cosmic time, demonstrating that what is unseen is just as essential as what is visible in defining the Virgo supercluster. Dark matter forms the scaffolding, intergalactic gas mediates interactions, and galaxies move within this framework, tracing paths dictated by forces beyond immediate perception. Observing these components, understanding their influence, and modelling their interactions provides insight into the supercluster's structure, dynamics, and evolution. Every observation we make of the Virgo supercluster is a journey through both space and time, because light travelling from those distant galaxies takes millions of years to reach us. The photons that arrive at our telescopes carry information about stars, gas, and motion as they existed tens of millions of years ago. When we look at the core of the Virgo cluster, the light we see left those galaxies long before humans appeared on Earth, before complex life evolved, and long before our planet took the form we recognise today. In this way, observing the supercluster is not merely an act of seeing, but a connection across epochs, linking our present with a distant past in which the structures we observe were already in motion, already evolving along their gravitational paths. The finite speed of light has profound implications for how we perceive galaxies. A galaxy located 50 million light-years away in the Virgo cluster appears to us as it was 50 million years ago. Its stars have aged, its gas has shifted, and its structure may have changed since that light began its journey. Yet the photons we detect preserve a snapshot, frozen in time, allowing astronomers to reconstruct motion, measure distances, and model interactions. Each observation, therefore, is a historical record, providing insight into the past behaviour of galaxies, clusters, and the supercluster as a whole. Even galaxies closer to us demonstrate this principle. Within the local group, the Andromeda Galaxy, only 2.5 million light-years away, is seen as it existed 2.5 million years ago. While this may seem short in cosmic terms, it is still long enough for significant events to have occurred, including stellar evolution, star formation, and orbital motion. Observing light from more distant regions of the Virgo supercluster magnifies this effect. Photons originating from the outskirts may take over 100 million years to reach us, presenting a picture of the supercluster's structure and motion at a vastly earlier point in its history. The journey of light is influenced by the mass distribution within the supercluster. Gravity bends light slightly, a phenomenon known as gravitational lensing, which can magnify, distort, or create multiple images of distant galaxies. Observing this lensing allows astronomers to map dark matter and infer the presence of massive structures, even when the matter itself is invisible. Light from galaxies is therefore not just a passive messenger, but a probe, responding to the gravitational influence of both visible and unseen components. Through these distortions, we can detect the hidden scaffolding that shapes the motion and structure of the supercluster. Intergalactic gas also affects the propagation of light. Photons passing through hot, ionized gas can be absorbed or scattered, particularly at specific wavelengths. This interaction provides additional information about the density, temperature, and composition of the medium between galaxies. By analysing the way light is altered as it travels across millions of light years, astronomers can reconstruct the distribution of intergalactic gas, map filaments, and understand how the supercluster's invisible components influence the galaxies moving within it. Light also carries information about motion through the Doppler effect. When galaxies move toward or away from us, their spectral lines shift slightly, allowing astronomers to measure velocity. These shifts reveal not only individual galaxy motion, but also the flow of groups and clusters along filaments. Within the Virgo Supercluster, redshift measurements show the coherent motion of subclusters and the drift of the local group toward the Virgo cluster. This demonstrates that light is both a messenger of distance and a record of motion, encoding the dynamic evolution of the supercluster over millions of years. The sheer distances involved highlight the scale of the supercluster. Light travelling from the central Virgo cluster takes roughly 50 million years, meaning the snapshot we observe predates the rise of modern mammals on Earth. Galaxies at the outer edges of the supercluster send photons that began their journey over 100 million years ago, providing a window into a distant and earlier state of the universe. Even the fastest astronomical instruments cannot observe galaxies as they exist now, because the speed of light sets a fundamental limit on perception. Every observation is inherently historical, connecting us to epochs far beyond our human timescale. Within clusters, light also traces interactions. Tidal streams colliding galaxies and bursts of star formation emit photons that traverse millions of light years, allowing astronomers to study the evolution of structures over time. Observing these features reveals patterns in motion, the influence of gravity, and the history of mergers. Each photon carries information about past events, making light a tool for reconstructing the choreography of the supercluster, showing how galaxies interact, move, and transform across both space and time. The journey of light also emphasizes the interconnectedness of the supercluster. Galaxies that appear close in projection may be separated by tens of millions of light years along the line of sight, and the photons we detect arrive simultaneously only because of the finite speed of light. Mapping these distances and motion allows astronomers to reconstruct three-dimensional structures, revealing the spatial arrangement of clusters, subclusters, and filaments. The light effectively bridges the gaps, providing a way to perceive the supercluster as an integrated system rather than a scattered collection of galaxies. Even small, faint galaxies contribute to this historical record. Dwarf galaxies, satellite systems, and intergalactic clouds emit photons that travel the same immense distances as light from giant ellipticals and spirals. These faint sources reveal motion, interaction, and distribution, allowing astronomers to trace the gravitational influence of nearby clusters, the paths of tidal streams, and the alignment of filaments. Light from these sources completes the picture, emphasizing that the history encoded in photons is rich, complex, and multi-layered. Observing light from millions of light years away also reveals the evolution of star formation. Many galaxies within the Virgo supercluster formed stars at higher rates in the past than they do today. Photons from these epochs capture regions of intense activity, showing bright clusters of young stars and active star-forming regions. Studying these light signatures allows astronomers to trace changes in star formation rates, gas depletion, and galactic growth over tens of millions of years. In this way, light becomes a window into both the motion and the life cycles of galaxies, bridging the gap between past and present. The distance light travels also highlights the finite speed of information across the universe. Even though galaxies are influenced by one another through gravity, these interactions are not instantaneous. Gravitational influence propagates at the speed of light, meaning that effects from distant clusters take millions of years to influence galaxies on the periphery of the supercluster. Observing light from these systems provides a simultaneous measure of both position and the delayed effect of forces, revealing the complexity of motion, interaction, and evolution within the supercluster. Even within the local group, light demonstrates its dual role as a messenger and a record of time. Observations of Andromeda, Triangulum, and nearby dwarf galaxies allow us to measure motion, trace past interactions, and predict future mergers. Scaling this understanding to the Virgo supercluster emphasizes how light connects us to every member galaxy, from dense central clusters to remote, isolated systems at the edges. Photons travelling across millions of light years encode both distance and dynamics, providing a way to perceive the supercluster as a living system evolving over cosmic time. The interpretation of light also informs our understanding of dark matter. By studying the motion of galaxies as revealed by redshifts and gravitational lensing, astronomers can infer the distribution of invisible mass. Photons from background galaxies bend around massive structures in Virgo, producing distortions that reveal hidden halos of dark matter. These measurements show that the invisible components exert gravitational influence across vast distances, guiding galaxy motion and maintaining the coherence of the supercluster. Light, in this sense, illuminates not just visible matter, but the unseen forces shaping the cosmos. Even the faint glow of intergalactic gas contributes to our understanding. X-ray photons emitted from hot plasma between galaxies provide critical information about density, temperature, and distribution. Observing this radiation allows astronomers to map the environment within clusters, measure the total mass, and understand interactions that influence galaxy evolution. These invisible photons, traveling across millions of light years, complement visible light to provide a comprehensive view of the supercluster, emphasizing the importance of all sources of light in tracing structure and dynamics. Every photon arriving at our telescopes or detectors represents a journey through the gravitational framework of the supercluster, guided along filaments, influenced by clusters, and shaped by invisible mass. Observing this light allows us to reconstruct motion, measure distance, map structure, and connect our present experience to events that unfolded tens of millions of years ago. When we begin to consider the Virgo supercluster in terms of time and scale, the mind naturally struggles to reconcile the immense distances, slow motions, and billions of years of evolution all occurring simultaneously. Every galaxy, from the largest ellipticals at the cluster's core to the tiniest dwarfs on the outskirts, traces a history measured in millions or even billions of years. Each orbit, each interaction, and each drift along filaments is part of a timeline that far exceeds human experience. In this context, time is inseparable from space. Light from these galaxies, travelling across tens of millions of light years, presents a view of events long past, allowing us to perceive the motion and evolution of the supercluster across epochs. Observing Virgo is therefore not just seeing space, but seeing time itself, unfolding at a scale that dwarfs any terrestrial or even solar system measure. Distances within the supercluster magnify the perception of time. A photon emitted from a galaxy in the Virgo cluster's core began its journey 50 million years ago. Over that span, stars have lived and died, galaxies have interacted, gas has moved along filaments, and dark matter has shifted under gravity's influence. Even the paths of small dwarf galaxies orbiting larger members have evolved, subtly altering positions and interactions. Observing these photons is like looking back into a history that unfolded long before the Earth existed in its present form, providing insight into motion, mass distribution, and gravitational dynamics that have shaped the supercluster for eons. The concept of scale also transforms when we consider the Milky Way in relation to the supercluster. Our galaxy spans roughly 100,000 light-years, a staggering distance by human standards, yet it is just a single node in a structure over 100 million light-years across. The local group, which contains the Milky Way and its companions, is tiny by comparison, yet it moves collectively toward the Virgo cluster, influenced by the gravitational pull of the supercluster's dense core. This motion, taking millions of years to progress even a small fraction of the supercluster, reminds us that scale and time operate differently in the cosmos. Distances that seem abstract are intimately tied to the slow but persistent evolution of the system. Within clusters, time is equally significant. Galaxies orbiting the central mass of the Virgo cluster complete rotations on timescales of hundreds of millions of years. Interactions between neighbouring galaxies, including mergers, tidal stripping, and bursts of star formation, unfold gradually, often unnoticed except through careful measurement. These processes accumulate over billions of years, producing the morphology, motion, and composition we observe today. Time and scale are therefore inseparable, each defining the other. Vast distances create long time scales, and slow motions over immense scales shape the supercluster structure. Even the smallest components of the supercluster, like dwarf galaxies, are part of this temporal and spatial framework. Their orbits, interactions, and eventual mergers reflect the influence of gravity across immense scales and time spans. Observing these tiny galaxies, both their position and velocity, allows astronomers to reconstruct the history of the larger supercluster. The past, present, and projected future of the Virgo supercluster are embedded in these motions, encoded in every photon travelling across millions of light years to reach our instruments. The concept of scale is amplified by the filaments connecting clusters. These vast bridges stretch tens of millions of light years, channeling galaxies, gas, and dark matter toward denser nodes. Galaxies moving along filaments travel slowly relative to the distances they cross, often taking millions of years to progress significant fractions of a filament. Observing these flows highlights both the vastness of space and the persistence of time, showing how gravitational forces operate continuously yet subtly, guiding motion over epochs that are nearly impossible to comprehend in human terms. Light itself emphasizes the interplay of time and scale. Photons from the Virgo cluster's outer reaches take over 100 million years to reach Earth, showing the supercluster as it existed far in the past. Each observation is a glimpse into a stage of evolution long gone, yet still physically influencing the motion of galaxies and clusters today. Measuring the light, mapping distances, and calculating velocities allows astronomers to reconstruct the timeline of the supercluster, connecting past events to present structures and predicting the gradual changes that will unfold in the future. Even on smaller scales, the passage of time within clusters shapes structure. Galaxies orbit multiple times over billions of years, interactions accumulate, and mergers slowly transform morphology. Spiral galaxies may lose gas, forming new stars in bursts, while ellipticals dominate the dense cores, shaped by countless interactions. Dwarf galaxies are absorbed, stripped, or scattered into tidal streams. These processes operate continuously, creating a living, evolving system that demonstrates how time and scale are woven into every aspect of the supercluster. The Milky Way's trajectory also reflects time and scale. While orbiting within the local group, our galaxy moves toward the Virgo cluster, influenced by the cumulative gravitational pull of distant clusters, filaments, and dark matter. The motion is slow, yet persistent, unfolding over millions of years. Satellite galaxies orbiting the Milky Way follow their own trajectories, affected by tidal forces and past interactions, illustrating that even small systems are part of the vast temporal framework of the supercluster. Gravity amplifies the significance of time and scale. Orbital periods of galaxies, the motion along filaments, and the merging of subclusters all reflect cumulative gravitational influence acting across immense distances and epochs. Clusters attract matter from the surrounding region, filaments guide flow, and dark matter provides the invisible scaffolding for motion. Over time, these forces shape the Virgo supercluster into a coherent system, maintaining the structure despite the expansion of the universe. Observing these dynamics requires understanding both the distances involved and the timescales over which motion occurs. Even the apparent emptiness of voids highlights the importance of scale. These low-density regions separate filaments and clusters by tens of millions of light years. Galaxies within voids experience minimal interactions, yet their motion is still influenced by distant clusters and filaments. Over millions of years, these subtle forces accumulate, slowly guiding galaxies toward denser regions and shaping the large-scale structure of the supercluster. The interplay of emptiness, density, motion, and time demonstrates the complex relationship between scale and the evolution of cosmic structures. The combination of time and scale also affects how astronomers model the supercluster. Simulations must account for billions of years of gravitational interactions, the flow of matter along filaments, and the evolution of clusters and galaxies. Observations of light provide snapshots that, when combined across many regions and distances, allow scientists to reconstruct the history and predict future motion. These models demonstrate that scale cannot be considered without time, and that time is inseparable from the spatial extent of the system. Even in the local group, time and scale are evident. The Milky Way and Andromeda are on a collision course, a future event billions of years away. Their past interactions with smaller galaxies have shaped both structure and motion, leaving streams of stars as evidence. Scaling this understanding to the Virgo Supercluster highlights the vast distances and times involved. Entire clusters move and interact over tens of millions of years. Filaments guide matter, and the supercluster continues to evolve under the influence of gravity, dark matter, and cosmic expansion. Observing the Virgo supercluster in terms of time and scale emphasizes our position as participants and observers. The supercluster's structure, motion, and evolution are all encoded in light travelling across millions of years, in the slow but relentless pull of gravity, and in the hierarchical organisation of clusters, subclusters, and filaments. By understanding these elements, we can perceive the dynamic processes that define the supercluster, connecting the Milky Way to its larger cosmic environment and providing a framework for exploring how these processes continue to shape the universe over epochs far beyond human experience. Even from our relatively small corner of the cosmos, it is possible to sense the gravitational influence of the Virgo supercluster on surrounding galaxies, clusters, and groups, illustrating that its role in the local universe extends far beyond its own boundaries. The supercluster acts as a massive node in the cosmic web, a focal point toward which matter slowly drifts along filaments, guided by gravity over tens of millions of light years. Our local group, which contains the Milky Way, is one of many smaller systems subtly drawn toward the Virgo cluster, moving through space along pathways shaped by the supercluster's immense mass. Observing this motion provides a perspective on the interconnectedness of cosmic structures, showing that the influence of Virgo is both local and far-reaching. Nearby galaxy groups, such as the M81 group and the Centaurus A group, are similarly affected by Virgo's mass. Though separated by millions of light years, the gravitational pull of the dense clusters within the supercluster guides their motion, aligning their trajectories with filaments that connect them to Virgo. Over millions of years, these small movements accumulate, gradually drawing groups closer to the denser regions and influencing the overall structure of the local universe. Even galaxies that appear isolated are subtly guided by the collective mass of the supercluster, demonstrating the pervasive reach of Virgo's gravitational influence. Clusters within the supercluster play a crucial role in this process. Dense regions, such as the central Virgo cluster, exert a stronger gravitational pull, shaping the motion of surrounding subclusters and groups. Galaxies in peripheral clusters slowly drift toward the centre, often along filaments that serve as pathways through space. This motion is slow on human timescales but measurable, and it affects the distribution, alignment, and interaction of galaxies across the supercluster. The result is a coherent system in which even distant galaxies are connected to the dynamics of Virgo, emphasizing the supercluster's role as a central organizer of motion in the local universe. The local group's motion toward Virgo highlights the supercluster's influence. Traveling at roughly 1,100 kilometers per second relative to the cosmic microwave background, the local group is gradually approaching the Virgo cluster. This drift is a cumulative result of gravitational interactions over millions of years, influenced by the combined mass of clusters, subclusters, filaments, and dark matter halos within the supercluster. Observing this movement not only demonstrates the power of gravity, but also provides a measure of the supercluster's total mass, showing how Virgo's influence extends across vast distances, connecting multiple groups and clusters in a slow but continuous gravitational flow. Filaments extending from the central cluster further illustrate Virgo's role. These structures channel galaxies, gas and dark matter toward the supercluster's dense nodes, shaping the distribution of matter across millions of light years. Galaxies travel along these filaments, following paths determined by both the visible massive clusters and the invisible framework of dark matter. In this way, Virgo exerts a guiding influence on motion across the local universe, orchestrating the slow migration of galaxies and subclusters toward regions of higher density. The alignment of these filaments and their gravitational pull emphasize that the supercluster functions as a central hub, linking distant systems in a coherent pattern of motion and structure. Interactions between clusters within Virgo also contribute to its role. Subclusters and smaller groups gradually merge with central clusters, redistributing mass, triggering star formation, and altering trajectories. These mergers occur over millions of years, creating the dense core observed in the Virgo cluster today. Observing these processes provides insight into how the supercluster grows, evolves, and influences its surroundings. Even the most distant galaxies feel this influence indirectly, as the cumulative gravitational field guides their motion and positions relative to the supercluster's central mass. The distribution of mass in Virgo determines its gravitational reach. Central clusters, massive ellipticals, and dark matter halos collectively generate a pull that extends far beyond the supercluster itself. Surrounding groups and clusters experience this influence subtly, slowly adjusting their paths over millions of years. These motions are measurable through redshift surveys, which reveal not only velocities toward or away from the Milky Way, but also the larger flow patterns connecting groups to Virgo. The supercluster's gravitational dominance thus defines its role in the local universe, shaping both structure and motion across enormous scales. Even the faintest dwarf galaxies are affected by Virgo's gravity. While small in mass, their motion is guided by the cumulative influence of clusters, filaments, and dark matter. Streams of stars and tidal debris, often generated through interactions, trace these gravitational pathways, providing evidence of Virgo's reach. Studying these features allows astronomers to reconstruct the supercluster's influence on its surroundings, revealing the interdependence of galaxies, clusters, and filaments in the larger structure of the local universe. The hot intergalactic gas within and around clusters also participates in Virgo's influence. This plasma interacts with moving galaxies, stripping gas from some systems while compressing it in others, triggering star formation or halting it depending on location. The distribution of gas mirrors the mass distribution, highlighting dense nodes, filaments, and voids. By observing X-ray emission, astronomers gain insight into the supercluster's mass, gravitational potential, and dynamic processes, reinforcing the idea that Virgo is both a source of influence and a structure shaped by the motion of matter within and around it. Dark matter amplifies the effect of mass on motion. Filaments of dark matter, extending from clusters, guide galaxies over millions of light years, shaping orbits, interactions, and group alignments. Even galaxies at the edges of the supercluster are subtly drawn along these invisible pathways, their motion tracing the gravitational structure of Virgo. Observations of lensing, galaxy motion, and large-scale surveys confirm that dark matter dominates the mass budget, ensuring that Virgo's influence reaches across the local universe, connecting galaxies, groups, and clusters in a coordinated, coherent pattern. The cumulative effect of these forces is a slow but measurable flow of galaxies toward the supercluster. Over tens of millions of years, groups drift, subclusters merge, and isolated galaxies adjust their trajectories. This motion, dictated by gravity and guided along filaments, creates a sense of order in an otherwise vast and complex universe, Observing this flow allows astronomers to understand the mass distribution within Virgo, the structure of the cosmic web, and the supercluster's influence on surrounding systems. Even the Milky Way's gradual movement toward Virgo is a tangible demonstration of these forces in action. Local clusters outside Virgo also reveal the supercluster's role. Systems such as the Fornax cluster or the Leo cluster show motion patterns influenced by Virgo's mass, aligning along filaments or accelerating slightly toward its dense regions. These subtle effects accumulate over cosmic timescales, producing coherent flows across tens of millions of light-years. The supercluster's central cluster acts as a gravitational anchor, while filaments guide peripheral groups, reinforcing the interconnectedness of the local universe and demonstrating how Virgo functions as a dominant structural and dynamic node. Observing these patterns emphasizes the hierarchical nature of cosmic structure. The Milky Way resides within the local group, which is part of a filament connecting to Virgo. Virgo itself contains clusters, subclusters, and filaments, all governed by gravity. Beyond it, other superclusters and voids exist, but the influence of Virgo dominates the immediate local universe. This hierarchy ensures that motion, structure, and evolution are coordinated across scales, linking galaxies, groups, and clusters into a single interconnected system. The interaction of motion, mass, and distance also highlights timescales. Galaxies require millions of years to traverse the supercluster's filaments, while clusters merge over tens or hundreds of millions of years. Even smaller groups orbiting the supercluster experience gradual shifts in trajectory that accumulate over epochs. Observing this motion reveals a dynamic universe in which Virgo plays a central role, guiding the evolution of systems across space and time and maintaining a coherent pattern despite the vast distances and complexity. The task of mapping the Virgo supercluster begins with a recognition of both its immensity and its complexity, because every galaxy, filament, and cluster contributes to a three-dimensional structure that stretches across tens of millions of light-years. Astronomers cannot simply point to the sky and trace its boundaries with the naked eye. Instead, mapping requires careful measurement, observation, and the integration of multiple techniques to understand how mass, motion, and position interconnect. From the local group, we're observing the supercluster from the outside, yet our perspective is limited by distance and the finite speed of light, meaning that every photon carries information about a past state of the universe. Reconstructing the full layout is therefore an exercise in both precision and imagination, combining observable evidence with models that account for unseen mass and motion over cosmic time. Redshift surveys form one of the primary tools for mapping the supercluster. By measuring the shift of light from galaxies, astronomers can determine both distance and velocity, establishing three-dimensional positions within the supercluster. These measurements reveal the relative motion of galaxies along filaments, within clusters, and across subclusters. Combined with observations of galaxy types and density, redshift surveys provide a framework for understanding the distribution of matter, identifying dense regions, and tracing the paths along which galaxies are moving. Without this technique, the Virgo supercluster would remain a flat two-dimensional pattern, lacking depth and context. Gravitational lensing offers another vital method. When light from distant galaxies passes near a massive cluster within Virgo, its path is bent, producing distortions, magnification, or even multiple images. By analysing these distortions, astronomers can infer the presence and distribution of dark matter, which dominates the mass of the supercluster. These invisible components, though not directly observable, are essential for mapping the supercluster's true structure. Combining lensing data with galaxy surveys produces a more complete picture, showing both the visible galaxies and the dark matter scaffolding that organises them. X-ray observations also contribute to mapping efforts. Hot, ionized gas within clusters emits X-rays, revealing the location, density, and mass of intergalactic plasma. Observing these emissions highlights regions of dense clusters, showing where gravitational potential wells are deepest and where interactions between galaxies are most frequent. This gas, combined with visible galaxies and dark matter distributions, provides a multi-layered view of the supercluster, illustrating how components interact and how structure is maintained over millions of light years. Filaments, though faint and difficult to observe directly, are revealed through the clustering of galaxies and the motion of matter along these pathways. Mapping filaments requires integrating galaxy positions, velocities, and density patterns, allowing astronomers to trace the invisible highways along which matter flows toward dense nodes. Within the Virgo Supercluster, filaments connect the central Virgo cluster to surrounding groups and subclusters, forming a coherent network that defines the supercluster's overall shape. These structures are crucial for understanding how matter is organized and how the supercluster evolves over cosmic time. Distance measurement is central to accurate mapping. Techniques such as Cepheid variables, supernova observations, and standard candles provide reliable measures for individual galaxies, anchoring the redshift data and confirming three-dimensional positions. By combining multiple methods, astronomers reduce uncertainty and create a more precise map of the supercluster, showing not only the location of galaxies, but also the paths along which they move. This process highlights the scale of the system. Distances measured in tens of millions of light years, with structures and motions extending across hundreds of millions of cubic light years of space. Even small galaxies and dwarf systems contribute to the map. These faint members are often difficult to detect, but their positions and velocities provide essential information about mass distribution, gravitational potential, and motion within clusters. Streams of stars and tidal debris created by interactions also trace gravitational influence, acting as markers that reveal the dynamics of the supercluster. Including these smaller components ensures that the map reflects the true complexity and hierarchy of Virgo, showing the relationships between massive clusters, subclusters, and individual galaxies. The hierarchical organization of the supercluster becomes apparent through mapping. Clusters within clusters, subclusters orbiting larger nodes, and galaxies travelling along filaments all form a nested structure that extends across immense distances. Mapping reveals this hierarchy, showing how local interactions contribute to the overall dynamics, and how smaller systems are influenced by the gravitational pull of larger structures. The supercluster is therefore not a uniform or random assembly, but a carefully organized dynamic system, with clear patterns and relationships observable through precise measurement. Time is also a critical factor in mapping. Light from distant regions arrives at different times, showing the supercluster at various stages of evolution. Combining observations from different distances allows astronomers to reconstruct motion, interaction history, and potential future trajectories. This temporal layering adds depth to the map, revealing the evolution of clusters, the growth of filaments, and the motion of galaxies over millions of years. Observing Virgo in this way highlights the dynamic nature of the supercluster, emphasizing that structure and motion are ongoing, continuous processes. Mapping also illustrates the influence of gravity on scale and distribution. Dense clusters attract matter from surrounding regions, subclusters move toward larger nodes, and galaxies along filaments follow gravitationally defined paths. Observing these patterns allows astronomers to infer mass distribution, identify dark matter concentrations, and predict future motion. The map is therefore both descriptive and predictive, showing not only what exists but also how the system will evolve over millions of years. Even regions that appear empty, the voids separating clusters and filaments, are important for mapping. These low-density areas provide context, showing the contrast between dense nodes and surrounding space. By defining these boundaries, astronomers can more accurately trace the shape and extent of the supercluster, understanding the flow of matter from sparse regions toward concentrated clusters. Mapping voids highlights the interconnectedness of all components, revealing how even empty space contributes to the supercluster's structure and evolution. Dark matter mapping is particularly revealing. Gravitational lensing combined with galaxy motion shows that most of the supercluster's mass is invisible. This unseen mass not only binds clusters and filaments, but also shapes the paths of galaxies over millions of light years. Observing how galaxies move relative to predicted positions allows astronomers to trace dark matter distribution, revealing the invisible framework that underlies the visible supercluster. Mapping this component is essential for a complete understanding of Virgo, showing how what we cannot see governs the motion and structure of what we can. Mapping the Virgo supercluster is a continuous process. New galaxies are discovered, faint filaments are traced, and mass distributions refined. Surveys such as the Sloan Digital Sky Survey provide massive data sets, while instruments measuring X-rays, infrared, and gravitational lensing add layers of information. Each measurement refines the map, revealing previously unseen connections, adjusting distances, and improving the understanding of motion and mass. The resulting maps show a dynamic, interconnected system, illustrating the complexity, hierarchy, and evolution of the supercluster. Even the motion of the local group contributes to mapping efforts. Our trajectory toward the Virgo cluster, combined with redshift surveys of neighbouring groups, provides a reference frame for understanding the flow of galaxies. By measuring relative motion and combining observations from multiple vantage points, astronomers can construct a more accurate three-dimensional map, capturing both position and motion across millions of light years. This perspective emphasizes that mapping is not just about static positions, but also about dynamic relationships, showing how galaxies interact within the gravitational framework of the supercluster. Mapping the supercluster emphasizes the vastness and interconnectedness of the Virgo region. Clusters, subclusters, filaments, and voids all combine to form a coherent, hierarchical and dynamic structure. Through careful observation, measurement, and analysis, astronomers reveal not only the distribution of galaxies, but also the influence of invisible components, the paths of motion, and the evolution of the system over millions of years. Mapping allows us to understand the supercluster as a living, evolving entity, a network of motion, gravity, and mass. Even as we explore the Virgo supercluster in detail, it becomes clear that placing it in context with other superclusters helps us appreciate its scale, structure, and influence. Superclusters exist throughout the universe, varying widely in size, mass, density, and composition, yet they share fundamental characteristics: hierarchical organization, gravitational coherence, and a connection to the cosmic web. Comparing Virgo to these other structures provides perspective, showing that while Virgo is immense and influential in the local universe, it is one of many nodes in a larger interconnected cosmic network. Each supercluster, though unique, follows similar principles, with galaxies, clusters, filaments, and dark matter forming a coherent and evolving system. The local supercluster, often used synonymously with the Virgo supercluster, is comparatively modest when placed alongside larger structures such as the Laniakea supercluster. Laniakea spans over 500 million light-years and contains tens of thousands of galaxies, including the Milky Way and Virgo itself. While Virgo acts as a dominant node within its local region, Laniakea shows that our immediate cosmic neighbourhood is part of an even larger network, illustrating the layered nature of structure in the universe. Comparing Virgo to Laniakea highlights not only scale, but also connectivity, demonstrating that the supercluster's influence extends outward and participates in the dynamics of larger structures. Other nearby superclusters, such as the Coma supercluster, provide additional points of comparison. The Coma supercluster is more massive and densely packed than Virgo, containing thousands of galaxies concentrated in a core cluster, along with extensive filaments. While Virgo is relatively irregular in shape, Coma demonstrates a more symmetrical configuration, reflecting differences in formation history, mass distribution, and local environment. Observing these differences allows astronomers to understand how superclusters evolve, how mass influences structure, and how galaxies respond to differing gravitational environments. Each comparison reveals variations in density, hierarchy, and motion, illustrating the diversity of superclusters within the local universe. Filament structure also varies between superclusters. Virgo is characterized by multiple connecting filaments that link clusters and subclusters, guiding the motion of galaxies and shaping the overall layout. In other superclusters, filaments may be longer, denser, or more numerous, creating differences in how galaxies flow, how clusters merge, and how voids are defined. Comparing these features provides insight into the mechanisms of large-scale structure formation, showing how gravity, dark matter, and cosmic expansion interact to create unique configurations across the universe. These variations emphasize that while the principles underlying superclusters are universal, the outcomes are diverse, producing structures of remarkable individuality. Density and mass distribution also reveal contrasts. Virgo's central cluster is dense, but its overall supercluster is less massive than some larger counterparts. In contrast, massive superclusters such as Shapley or Hercules contain clusters with higher densities and greater gravitational influence, affecting motion across wider regions. Observing the differences in mass highlights how superclusters shape the local universe, influencing nearby groups, guiding filaments, and controlling the flow of galaxies across millions of light years. Comparisons like these help situate Virgo within a broader cosmic landscape, showing both its prominence locally and its relative modesty on the larger scales. Observing galaxy populations further distinguishes superclusters. Virgo contains a mix of spirals, ellipticals, and irregular galaxies, with ellipticals dominating the dense central cluster. Other superclusters may have cores dominated by massive ellipticals, fewer spirals, or differing ratios of dwarfs to larger galaxies. These differences reflect variations in formation history, environment, and local interactions. Comparing galaxy populations across superclusters reveals patterns of evolution, star formation, and merger activity, providing insight into how environment shapes the development of galaxies over cosmic time. The velocity and motion of galaxies also differ between superclusters. In Virgo, the local group and surrounding groups are slowly moving toward the central cluster along filaments, influenced by mass concentrations and dark matter. In more massive or densely packed superclusters, these motions can be more rapid, with galaxies interacting more frequently, merging more often, and following more coherent flows. Comparing these dynamics allows astronomers to understand the influence of scale, density, and gravitational potential on galaxy behavior, illustrating that each supercluster's character is defined by the interplay of mass, motion, and structure. Even the role of dark matter varies. Virgo's dark matter halos provide the scaffolding for clusters, subclusters, and filaments, but in larger superclusters, the distribution may be more extensive, linking nodes across greater distances. This additional mass affects galaxy motion, orbital dynamics, and the formation of clusters over cosmic time. Comparing the invisible components between superclusters highlights their significance in shaping both structure and motion, emphasizing that what is unseen governs much of the behavior observed in visible galaxies. Time also factors into comparison. While Virgo shows the effects of millions of years of gravitational interaction, other superclusters may exhibit evidence of earlier or later formation, with differing merger histories and cluster evolution. Some superclusters are more mature, with dense cores, frequent mergers, and stabilized filaments, while others are more diffuse or actively accreting new groups. Studying these temporal differences provides context for Virgo's current state, revealing how superclusters evolve differently depending on mass, environment, and local interactions. The layout of voids differs as well. Virgo is surrounded by relatively sparse regions, creating contrast between dense clusters and emptier areas. Other superclusters exhibit larger or more structured voids, affecting the flow of galaxies and the organization of filaments. Comparing these regions allows astronomers to understand how empty space influences motion, mass accumulation, and the coherence of the overall structure. It also emphasizes the importance of scale, as even voids spanning tens of millions of light-years contribute to the organization and evolution of superclusters. Galactic interactions also differ. In Virgo, interactions are concentrated in the dense central cluster, while in more massive superclusters, interactions may occur over larger volumes or involve multiple clusters simultaneously. Observing these differences allows astronomers to trace the impact of density, mass, and scale on the evolution of galaxies, showing how environment shapes star formation, mergers, and morphology. Each supercluster offers a unique laboratory for studying the processes that govern galaxies over cosmic time. Mapping and comparing superclusters is therefore essential for understanding the universe. Virgo's structure, while significant locally, is part of a continuum of superclusters that collectively shape the large-scale organization of matter. Observing, measuring, and comparing these structures provides insight into the mechanisms of formation, the influence of dark matter, the flow of galaxies, and the evolution of cosmic architecture. Each supercluster contributes to the interconnectedness of the universe, revealing patterns that extend far beyond individual systems and demonstrating that, while Virgo is central locally, it is one of many players in a complex cosmic network. Even subtle differences in shape, mass distribution, and filament connectivity have profound implications. Virgo's irregular shape contrasts with more symmetrical superclusters, revealing the influence of past mergers and environmental conditions. Mass and density variations affect the velocity and motion of galaxies, shaping the overall dynamics and gravitational reach. By comparing these features, astronomers gain insight into the processes that govern both individual superclusters and the cosmic web as a whole, showing that variation is as fundamental as similarity in shaping the universe. Placing Virgo in the context of other superclusters emphasizes scale, hierarchy, and the interconnected nature of cosmic structure. While Virgo is influential in the local universe, it is part of a network of nodes and filaments that extend across hundreds of millions of light-years, linking galaxies, groups, and clusters in a coordinated yet dynamic system. Comparing Virgo to others highlights its strengths, limitations, and unique characteristics, illustrating that superclusters, while adhering to universal principles, exhibit diversity that reflects their environment, mass, history, and composition. Understanding the Virgo supercluster in isolation provides immense insight, yet stepping back to see the big picture reveals how it fits into the vast cosmic landscape. The supercluster is not a solitary structure. It is one node in a network of superclusters, filaments, clusters, and voids that together form the large-scale architecture of the universe. Each component, from the smallest dwarf galaxy to the densest cluster core, plays a role in this intricate system, interacting with others through gravity, motion, and the unseen scaffolding of dark matter. Observing the supercluster from this broader perspective highlights the interplay of scale, mass, and connectivity that defines the universe as a coherent, evolving entity. The big picture shows that Virgo, while enormous, is part of a hierarchy of cosmic structure. Within the supercluster, clusters are nested within subclusters, filaments connect nodes across tens of millions of light-years, and voids provide space for matter to flow. Expanding further, Virgo itself is a component of the Laniakea supercluster, a massive region encompassing thousands of galaxies across hundreds of millions of light-years. From this vantage, it is evident that our local group with the Milky Way at its centre is just a small participant in a vast network of motion, interaction, and evolution, connected to distant galaxies through the invisible forces that shape the universe. Gravitational influence defines the relationships between these structures. Filaments act as highways, guiding galaxies toward dense nodes, while clusters pull smaller groups and isolated galaxies toward them. The distribution of mass, particularly dark matter, determines the flow of motion, the alignment of filaments, and the evolution of clusters. Observing the big picture emphasizes that the universe is organized, coherent, and hierarchical, even across scales so large that light requires millions of years to traverse the distances involved. Every motion within Virgo, every interaction, and every merger is part of a continuum that extends far beyond what we can see directly. Void regions, often overlooked, are critical for understanding the big picture. These low-density areas separate filaments and clusters, creating contrast that defines the structure of the supercluster network. Galaxies moving near these voids experience slower interaction rates, yet their motion is influenced by surrounding mass, causing them to drift along filaments toward dense nodes. These vast empty spaces also provide perspective, highlighting the scale of clusters, the reach of filaments, and the interconnectedness of superclusters across the universe. Mapping voids is as important as mapping dense regions because they reveal how matter flows and how the universe organizes itself over time. Light traveling across these immense distances further connects the big picture to time. Photons from the far edges of Virgo reveal the structure as it existed tens of millions of years ago, while light from more distant superclusters allows astronomers to trace motion, interaction, and evolution across hundreds of millions of light years. Each observation provides a snapshot frozen in time that, when combined with others, forms a three-dimensional map of the cosmic web. These light-based observations reveal patterns of connectivity, the influence of gravity, and the role of dark matter in shaping the large-scale structure, emphasizing that the universe is dynamic, hierarchical, and intricately connected. Comparisons to other superclusters help contextualize Virgo within the big picture. The Coma supercluster, for example, is denser and more massive, while Laniakea encompasses a wider region, linking Virgo to thousands of galaxies across a vast volume of space. Observing differences in mass, density, filament structure, and galaxy populations allows astronomers to understand both universal principles and local variation. Each supercluster contributes to the overall architecture of the universe, showing how matter organizes itself into coherent, interconnected systems that evolve over billions of years. Mass distribution is central to the big picture. Dense clusters anchor filaments, guide motion, and maintain the coherence of superclusters. Dark matter dominates, forming invisible halos that extend far beyond visible galaxies, influencing orbits and interactions. Even faint dwarf galaxies contribute to gravitational dynamics, shaping local flows and reinforcing larger patterns. The interplay of visible and invisible mass demonstrates that structure, motion, and evolution are inseparable, and that understanding the universe requires recognizing the role of every component, regardless of size or visibility. Observing motion within the supercluster and across neighboring structures illustrates the continuity of gravitational influence. Filaments channel galaxies toward dense nodes, clusters attract surrounding groups, and the cumulative effects of these forces shape trajectories across millions of light years. Even the local group is subtly influenced by these flows, moving toward the Virgo cluster along gravitational pathways. These patterns show that the big picture is dynamic. Superclusters, filaments, and voids interact continuously, evolving together as part of a larger cosmic system. Time and scale intersect in profound ways. Galaxies orbit, clusters merge, and filaments guide matter over millions of years. Yet the structure remains coherent, revealing the stabilizing influence of gravity. Observing these processes allows astronomers to reconstruct the evolution of Virgo and neighboring superclusters, trace motion along filaments, and predict future development. Time magnifies the effects of scale, showing that even slight motions accumulate to produce large-scale changes, shaping the supercluster's structure and the broader network of matter across the universe. Intergalactic gas also contributes to the big picture. Hot plasma within clusters emits X-rays, interacts with galaxies, and redistributes mass, affecting motion and evolution. Gas along filaments provides material for star formation and shapes galaxy morphology over time. These invisible components, in conjunction with dark matter, define the framework within which galaxies move and evolve. Observing these interactions highlights that the universe's structure is maintained through continuous processes, with both visible and invisible matter playing integral roles. The big picture also emphasizes connectivity. No supercluster exists in isolation. Filaments, voids, and gravitational influence link them, creating a network that spans hundreds of millions of light years. Virgo connects to neighboring superclusters, guiding motion and influencing the distribution of galaxies. Even seemingly isolated systems are part of this web, responding to the cumulative gravitational field of surrounding structures. Observing these connections reveals the universe as a cohesive, hierarchical system where every node, filament, and void contributes to the overall architecture. Hierarchical structure is evident at every scale. The Milky Way and its satellites form the local group, which participates in a filament toward Virgo. Virgo itself contains clusters, subclusters, and filaments, all interacting within the larger Laniakea framework. Beyond that, additional superclusters form nodes that extend the cosmic web, linking structures over hundreds of millions of light years. Understanding this hierarchy provides perspective on both motion and evolution, showing how small-scale dynamics within clusters relate to the larger flows of the universe. The big picture also informs predictions about the future. Virgo, along with neighbouring structures, will continue to evolve, clusters merging, filaments guiding motion, and voids reshaping flows. The Milky Way's trajectory toward the Virgo cluster is a small-scale example of this ongoing evolution, illustrating that the supercluster is dynamic, not static. Observing current motion, mass distribution, and interaction patterns allows astronomers to model future structure, revealing how the universe will continue to organize and evolve over billions of years. Finally, considering the Virgo supercluster in the context of the big picture emphasizes our place within the cosmos. Our galaxy is a small participant in a vast interconnected system, yet it is connected through gravity, motion, and light to countless other galaxies. Observing the supercluster and its relationships to neighbouring structures provides both a sense of scale and an understanding of cosmic order, showing that the universe is a dynamic, hierarchical, and interconnected system. Stepping back from the detailed exploration of the Virgo supercluster, it becomes possible to appreciate the enormity, complexity, and interconnectedness of the universe in a way that is both humbling and profound. The supercluster, with its thousands of galaxies, dense clusters, sprawling filaments, and vast voids, demonstrates that the cosmos is organized on scales far beyond human perception, yet governed by principles we can measure, observe, and understand. Every galaxy, from massive ellipticals to faint dwarfs, participates in this intricate system, influenced by gravity, dark matter, intergalactic gas, and the motion of neighbouring galaxies. Observing Virgo in this context encourages reflection on the relationships between space, time, and matter, showing how structure and motion are inseparably linked across cosmic scales. Even as the Milky Way appears central in our immediate experience, it is a small participant within the local group, which itself is only one of many groups within the Virgo supercluster. Our galaxy's orbit, the motion of its satellite systems, and the trajectory of the local group toward the Virgo cluster demonstrate that even modest scales in human terms are connected to the larger gravitational framework. the supercluster's influence reaches across millions of light years, guiding motion, shaping evolution, and maintaining coherence, providing a concrete example of how local and large-scale structures are intertwined. The cosmic web formed by dark matter, filaments, and clusters highlights the invisible yet essential components of this system. Gravity binds these elements together, guiding motion, influencing mergers, and dictating the flow of matter across vast distances. Intergalactic gas adds further complexity, interacting with galaxies, mediating star formation, and distributing mass throughout clusters and filaments. Observing these invisible elements emphasizes that the universe's structure is maintained by both visible and unseen forces, each playing a crucial role in shaping the evolution of the supercluster. Time itself is inseparable from the structure and motion of Virgo. Light traveling across tens of millions of light years carries information about past states, providing snapshots that, when combined, reveal motion, interaction, and evolution over immense timescales. Galaxies orbit, merge, and drift along filaments over millions of years, while clusters grow and subclusters merge. Understanding these timescales allows us to see the supercluster as a dynamic, evolving system, rather than a static arrangement of stars. Every observation we make is a glimpse into the past, a record of motion and structure encoded in photons that have travelled for millions of years to reach us. The scale of Virgo also illustrates the hierarchy inherent in cosmic structure. Individual galaxies are grouped into clusters. Clusters form subclusters, subclusters connect via filaments, and filaments extend across the supercluster, linking nodes in a coordinated, gravitationally coherent system. Beyond Virgo, neighbouring superclusters form a broader network, showing that the universe is organised across multiple scales, each nested within a larger framework. The Milky Way, while small, participates in this structure, following gravitational pathways along filaments toward dense nodes, influenced by both visible and invisible matter, and moving within a system that spans millions of light years in every direction. Observing motion within the supercluster emphasizes the subtlety and persistence of gravitational influence. Galaxies orbit cluster centers, move along filaments, and interact with neighbors in ways that accumulate over millions of years. Even small galaxies, dwarfs, and satellites contribute to the overall dynamics, influencing local flows and reinforcing the hierarchical organization. These motions demonstrate that the universe is not static, but a complex network of interacting systems, evolving slowly yet continuously, driven by the fundamental forces that shape matter on every scale. Comparing Virgo to other superclusters provides further context. While Virgo is influential locally, structures like the Laniakea supercluster or the Coma supercluster illustrate both the diversity and the universality of cosmic architecture. Differences in density, shape, galaxy populations, and filament connectivity reveal how environment, mass, and formation history influence structure. Yet the same principles, gravity, dark matter, and hierarchical organization apply throughout. This comparison underscores that our understanding of Virgo is part of a larger framework, situating the supercluster within a broader, interconnected cosmic landscape. Light travelling across the supercluster provides insight into both motion and evolution. Photons from the distant Virgo cluster reveal the system as it existed tens of millions of years ago, capturing the positions, interactions, and dynamics of galaxies, clusters, and filaments. Observations across different wavelengths, from optical to X-ray to infrared, allow astronomers to reconstruct mass distribution, motion, and structure, revealing the interplay between visible galaxies, dark matter, and intergalactic gas. These observations show that light is not merely a tool for seeing, it is a bridge across time, connecting our current perspective to events that unfolded long before the emergence of Earth or human civilization. The integration of all these elements, mass, gravity, motion, light, and time, creates a cohesive understanding of the supercluster. the hierarchy of clusters within clusters, the flow of galaxies along filaments, the distribution of invisible matter, and the drift of groups toward dense nodes all interact to maintain structure over cosmic time. Observing these relationships provides insight into both the current state of the supercluster and its evolution, highlighting that every component, from the largest cluster to the smallest dwarf galaxy, contributes to the orchestration of the system. Even seemingly empty voids play a role in the big picture. These regions of low density define boundaries, channel matter along filaments, and provide contrast to dense clusters, shaping motion and structure over millions of light years. Observing voids emphasizes that the universe is organized not only by what exists, but also by what is absent, and that emptiness is as integral to cosmic architecture as matter. The interplay of dense and sparse regions, of light and shadow, creates the framework within which the Virgo Supercluster and neighbouring structures evolve. The Milky Way's position within this vast system illustrates our perspective in the cosmos. While our galaxy may seem central in human experience, it is peripheral in relation to the supercluster's densest regions. Yet its location allows us to observe, measure and understand the structure, motion, and evolution of Virgo, providing a vantage point that balances proximity and separation. From this position, we can trace filaments, observe cluster dynamics, and measure motion, connecting our galaxy to the broader system in both space and time. Finally, reflecting on the Virgo supercluster invites consideration of scale, connectivity, and perspective. Thousands of galaxies, countless stars, dark matter halos, filaments, and voids together form an intricate and evolving system. Motion occurs slowly yet persistently. Light carries information across millions of years, and gravitational influence links every component in a coherent framework. Observing, mapping, and comparing these elements provides a sense of connection, showing that our galaxy, our local group, and the Virgo supercluster itself are participants in a universe defined by hierarchy, motion, and organization. This understanding of Virgo also prepares us to consider broader questions about cosmic evolution, the interplay of matter and gravity, and our place within an expanding universe. By observing how galaxies interact, how filaments guide motion, and how clusters merge, we gain insight into the processes that govern the formation and evolution of structure on the larger scales. In this sense, reflection is not passive, it is an engagement with the universe, connecting observation, understanding, and perspective across both space and time. Considering the supercluster as a whole, we see a dynamic network of interrelated systems, each affecting the others, each contributing to a pattern that stretches across tens of millions of light years. The Milky Way, part of the local group, participates in this network, moving slowly but inevitably toward the Virgo cluster, influenced by mass, gravity, and filaments. Observing this interaction reinforces the sense that our place in the universe is both connected and contextual, part of a hierarchy that extends from individual stars to the larger structures visible in the cosmos. Ultimately, the Virgo supercluster serves as a window into the universe's organization, revealing the principles that govern galaxies, clusters, filaments, and voids. By tracing light, mapping mass, observing motion, and considering time, we gain a holistic view of how matter organizes itself on the larger scales. Reflection on the supercluster provides not only understanding of structure and dynamics, but also a perspective on our own place in the cosmos, showing that even a small galaxy like the Milky Way is connected to a vast, evolving, and intricately organized universe.